Light travels at exactly 299,792,458 meters per second in vacuum. This number has no uncertainty, no measurement error, because since 1983, the meter has been defined as the distance light travels in 1/299,792,458 of a second. The speed of light became the definition rather than a measured quantity, fixing its value permanently. This speed, about 300,000 kilometers per second or 186,000 miles per second, represents the maximum velocity at which anything can travel through the universe. Not just light, but any particle, any information, any cause-effect relationship cannot exceed this limit. The first quantitative measurement of light speed came in 1676 from Ole Rømer, a Danish astronomer working at the Paris Observatory. Rømer studied the eclipses of Io, one of Jupiter's moons, noting that the timing of eclipses shifted depending on whether Earth was moving toward or away from Jupiter in its orbit. When Earth moved toward Jupiter, eclipses occurred slightly earlier than predicted. When Earth moved away, eclipses occurred later. Rømer attributed this timing shift to light's finite travel time. Light from Io took longer to reach Earth when Earth was farther away. Rømer calculated that light required about 22 minutes to cross the diameter of Earth's orbit around the Sunday. The actual value is closer to 16 minutes and 40 seconds, but Rømer's orbital diameter estimate was inaccurate. Using the correct orbital diameter of about 300 million kilometers and his observed timing shifts, modern recalculation of his data gives light speed around 220,000 kilometers per second, not far from the true value, considering the limitations of 17th century measurements. Rømer's work proved light traveled at finite speed rather than instantaneously, a revolutionary conclusion that contradicted centuries of assumption. For the next 2 centuries, astronomers refined this measurement using improved observations of Jupiter's moons and other astronomical phenomena. But terrestrial measurements remained impossible until the mid-1800s, when technology advanced sufficiently. In 1849, Hippolyte Fizeau in France performed the first successful Earth-based measurement using a rapidly rotating toothed wheel placed in front of a light beam. The beam traveled to a distant mirror 8 kilometers away and returned. By adjusting the wheel's rotation speed until the returning light passed through the next gap between teeth, Fizeau calculated light speed at 315,000 kilometers per second within 5% of the true value. Léon Foucault improved this technique in 1862, using a rotating mirror instead of a toothed wheel, achieving greater precision. His measurement gave 298,000 kilometers per second, much closer to the true value. But the landmark terrestrial measurements came from Albert Michelson, an American physicist who devoted much of his career to determining light speed with unprecedented accuracy. In 1879, while a young naval officer, Michelson conducted his first measurements using rotating mirrors and obtained 299,910 kilometers per second, accurate to within 0.04%. Michelson continued refining his measurements over decades. His 1,926 measurement, conducted between Mount Wilson and Mount San Antonio in California over a baseline of 22 miles, used an octagonal rotating mirror system in an evacuated tube to minimize air's effects. The result, 299,796 kilometers per second, accurate to within 4 kilometers per second. This remained the most precise direct measurement for decades. Michelson received the 1907 Nobel Prize in Physics, becoming the first American to receive a Nobel in Science, honored primarily for his precision, optical instruments, and measurements, including light speed determination. The speed of light in vacuum is the same regardless of the light source's motion or the observer's motion. Light from a flashlight on a speeding train travels at exactly the same speed as light from a stationary flashlight. This constancy seemed impossible under classical physics, where velocities add. If you're on a train moving at 100 kilometers per hour and throw a ball forward at 50 kilometers per hour relative to the train, someone on the ground sees the ball moving at 150 kilometers per hour. But light doesn't work this way. The light from your flashlight on the train moves at 299,792,458 meters per second relative to you, and the same 299,792,458 meters per second relative to someone standing on the ground. Velocities don't add for light. This constancy contradicted intuition and classical mechanics. How could light speed be independent of the source's motion? The answer required abandoning absolute space and time, replacing them with relative space and time that mix together differently for different observers. This revolutionary idea emerged from Albert Einstein's special relativity in 1905, but the groundwork was laid by experiments in the late 1800s that found light's speed stubbornly constant, regardless of Earth's motion through space. The speed limit applies not just to light, but to all massless particles. Photons, the particles of light, have no rest mass and always travel at exactly light speed, never faster or slower. Gravitons, the hypothetical particles mediating gravity, also have no mass and should travel at light speed if they exist. Gluons, which carry the strong nuclear force holding quarks together inside protons and neutrons, have no mass and travel at light speed. Any particle with zero rest mass must travel at exactly 299,792,458 meters per second. Particles with mass can approach light speed but never reach it, let alone exceed it. Why 299,792,458 meters per second specifically? Why not some other value? The answer lies in the fundamental properties of space itself. In classical electromagnetism, light speed equals 1 divided by the square root of the product of two constants, the electric permittivity of vacuum and the magnetic permeability of vacuum. These constants describe how electric and magnetic fields propagate through empty space. Their values determine light speed. But a deeper question remains: why do these constants have the values they do? That question leads to the structure of space-time itself and the fundamental architecture of physical law. The number 299,792,458 is arbitrary. In one sense, it depends on our choice of units, specifically the meter and second. In different units, light speed has different numerical values. Expressing light speed in furlongs per fortnight or astronomical units per year gives wildly different numbers. But the physical reality behind the number is not arbitrary. In natural units used in theoretical physics, light speed is often set to 1, making it a dimensionless reference. The real question isn't why the number is what it is, but why a maximum speed exists at all, and why all massless particles share that maximum. Light takes about 1.3 seconds to travel from Earth to the Moon, 8 minutes and 20 seconds to travel from the Sun to Earth, 5.5 hours to reach Pluto at its average distance, and 4.37 years to reach Proxima Centauri, the nearest star. The observable universe extends roughly 46.5 billion light-years. In all directions, the distance light has traveled while the universe expanded over its 13.8 billion-year history. This universal speed limit shapes everything from the structure of space-time to the scale of the observable universe to the impossibility of practical interstellar travel with conventional propulsion. Every measurement of light speed in vacuum by every technique, in every direction, at every time, has given the same result within experimental uncertainty. Laser interferometry, time of flight measurements, cavity resonance measurements, and astronomical observations all converge on 299,792,458 458 meters per second. This consistency across different methods and conditions validates the measurement and underscores light speed's fundamental nature. It's not a property of light specifically, but rather a property of space-time itself, the maximum rate at which cause and effect can propagate, the speed limit built into the universe's fabric, the Galilean transforms that worked until they didn't. In classical mechanics, velocities add according to common sense. If you're on a train moving at 30 meters per second and walk forward at 2 meters per second relative to the train, someone on the ground sees you moving at 32 meters per second. This simple addition is called the Galilean velocity transformation, named after Galileo Galilei, who described relative motion in the early 1600s. The formula is straightforward. Your velocity in the ground frame equals your velocity in the train frame plus the train's velocity. This works perfectly for everyday speeds, walking, driving, even jet planes traveling at hundreds of meters per second. Isaac Newton formalized this concept in his Principia Mathematica, published in 1687. Newton's laws of motion assumed absolute space, a fixed, unchanging background against which all motion occurs, and absolute time that flows at the same rate everywhere, regardless of motion. In Newton's universe, space and time are completely separate and independent. You can measure time with a clock, measure space with a ruler, and the measurements don't depend on how fast you're moving. Two observers, moving at different velocities, would disagree about positions and velocities, but would agree about time intervals and spatial separations. The Galilean transformation equations formalize this. If one observer measures an event at position x and time t, and a second observer moves at velocity v relative to the first, the second observer measures the same event at position x minus v times t, but at the same time t. Time is absolute, both observers agree on the time. Only positions differ, adjusted by the relative velocity. These transformations worked brilliantly for centuries, successfully predicting planetary motions, projectile trajectories, and every mechanical system physicists studied. Newton's mechanics, built on Galilean transformations, was the most successful scientific theory ever devised up to the 1800s. But in the 1,860 seconds, James Clerk Maxwell unified electricity and magnetism into a single theory of electromagnetism. Maxwell's equations, published in final form in 1865, described how electric and magnetic fields propagate through space. When Maxwell combined his equations in certain ways, he derived a wave equation showing that electromagnetic disturbances travel as waves. The wave velocity that popped out of the equations equaled 1 divided by the square root of the electric permittivity times the magnetic permeability. Plugging in measured values of these constants gave approximately 310,000 kilometers per second, suspiciously close to the measured speed of light. Maxwell realized light must be electromagnetic waves. This unification was a triumph light. Electricity and magnetism were manifestations of the same fundamental field. But the wave equation created a problem. The speed of light appeared as a constant in Maxwell's equations, derived from the properties of electric and magnetic fields. But constant relative to what? In Galilean relativity, velocities aren't absolute, they depend on the reference frame. A wave traveling at 300,000 kilometers per second in one frame should travel at 300,001 kilometers per second in a frame moving at 1 kilometer per second. Yet Maxwell's equations gave a single value independent of reference frame. This contradiction prompted physicists to propose the luminiferous ether, a medium filling all space through which electromagnetic waves propagate. Just as sound waves travel through air at a speed determined by air's properties, light waves would travel through ether at a speed determined by ether's properties. Light speed would be constant relative to the ether, not relative to the observer. An observer moving through the ether should detect different light speeds in different directions, just as someone moving through air detects different sound speeds depending on whether sound travels with or against the wind. The ether had to have peculiar properties. It filled all space, including the vacuum between stars and planets. It had to be rigid enough to support high-frequency electromagnetic waves, rigidity comparable to steel, yet completely transparent, and offering no resistance to objects moving through it. Planets orbit the Sun for billions of years without slowing down, despite supposedly ploughing through ether. The ether interacted with electromagnetic fields, but not with matter. These contradictions didn't initially trouble physicists, who assumed further research would resolve them. The key testable prediction: Earth orbits the Sun at about 30 kilometers per second, meaning Earth moves through the ether at this speed. Measuring light speed in the direction of Earth's motion should give a different value than measuring perpendicular to Earth's motion. The difference would be small, only about 0.01%, but detectable with sufficiently sensitive instrument. Albert Michelson designed an interferometer capable of detecting this difference in 1881, performing preliminary measurements in Berlin. The results were ambiguous, possibly showing a tiny effect, but far smaller than expected. Galilean transformations predict that Maxwell's equations should look different when transformed between reference frames moving at different velocities. Specifically, the speed of light should change. But Maxwell's equations stubbornly maintain the same form regardless of velocity, always predicting the same light speed. This suggested either Maxwell's equations were wrong and needed modification, or the Galilean transformations were wrong and needed modification. Most physicists, in the 1,880 seconds, suspected Maxwell's equations required adjustment. A few considered modifying the transformation laws themselves. Hendrik Lorentz, a Dutch physicist, developed transformation equations in 1892 that preserved Maxwell's equations form across different reference frames. These Lorentz transformations mixed space and time together in a velocity-dependent way. At low velocities, they reduced to Galilean transformations, explaining why Galilean relativity worked so well for everyday speeds. But at high velocities approaching light speed, space and time transformed in ways that kept light speed constant across all frames. Lorentz viewed these as mathematical conveniences, tricks that made calculations easier, not necessarily reflecting physical reality. George Fitzgerald in Ireland independently proposed in 1889 that objects contract along their direction of motion when moving through the ether, with contraction factor depending on velocity. This length contraction would exactly cancel the expected difference in light speed measurements, explaining why experiments failed to detect Earth's motion through ether. Combined with time dilation clocks slowing when moving through ether, Fitzgerald contraction could explain null result. But these explanations felt ad hoc, inventing special effects specifically to preserve the ether theory against contrary evidence. The crisis deepened in the 1,890 seconds as more precise experiments continued finding light speed constant regardless of motion. Either nature conspired to hide the ether through multiple compensating effects, or something fundamental was wrong with the conceptual framework. The Galilean transformations that had worked for 2 centuries suddenly seemed inadequate. Absolute space and time, the bedrock of Newtonian mechanics, appeared questionable. Physics stood at a crossroads: modify electromagnetism to fit classical mechanics, or modify classical mechanics to fit electromagnetism. Henri Poincaré, the great French mathematician and physicist, recognized the depth of the problem. In lectures and papers from 1898 to 1905, Poincaré suggested the impossibility of detecting absolute motion might be a fundamental principle, what he called the principle of relativity. If this principle held universally, it would require rethinking space and time. Poincaré came close to developing special relativity, but remained anchored to the ether concept, unable to fully abandon the classical framework. It took Einstein, less constrained by the classical tradition, to make the conceptual leap that resolved the contradictions. The Michelson-Morley experiment that found nothing. In 1887, Albert Michelson and Edward Morley conducted what's often called the most famous failed experiment in physics. Working at Case School of Applied Science in Cleveland, Ohio, they built an interferometer designed to detect Earth's motion through the luminiferous ether by comparing light speed in different directions. The experiment's precision was extraordinary, capable of detecting speed differences as small as a few kilometers per second. The expected difference based on Earth's 30 kilometer per second orbital velocity was about 9 kilometers per second, easily within the instrument's sensitivity. Yet the experiment detected nothing, no difference in light speed, regardless of direction. The interferometer split a light beam into two perpendicular beams using a half-silvered mirror. One beam traveled parallel to Earth's motion through the ether, the other perpendicular. After traveling equal distances, both beams reflected back and recombined. If light speed differed in the two directions, one beam would return slightly before the other, creating an interference pattern alternating bright and dark fringes. Rotating the apparatus 90 degrees should shift the interference pattern as the faster and slower directions swapped. The expected shift was about 0.4 fringe widths, clearly visible. The interferometer sat on a sandstone slab floating in a mercury trough to minimize vibrations. The light paths stretched about 11 meters, achieved by bouncing beams back and forth multiple times using mirrors. The entire apparatus could rotate smoothly while maintaining optical alignment, allowing measurements in all directions. Observations occurred in the basement of a brick building to maintain temperature stability and avoid air currents that might disturb the delicate interference patterns. Michelson and Morley spent months making measurements at different times of day and night, different seasons, ensuring any effect from Earth's motion would be captured. The null result was shocking. The interference pattern showed no significant shift when the apparatus rotated. The difference in light speed between perpendicular directions was less than 5 kilometers per second, much smaller than the expected 9 kilometers per second from Earth's orbital motion. Considering Earth's motion around the Sun's motion around the galaxy, and the galaxy's motion through space, some component of velocity through the ether should be detectable. Yet nothing appeared. Either Earth dragged the ether along with it, contradicting astronomical observations, or the ether didn't exist, or something more subtle was happening. Michelson and Morley published their results in the American Journal of Science in November 1887. They wrote that the result clearly negative, suggesting the hypothesis of a stationary ether was incorrect. But they didn't immediately abandon ether theory. Instead, they suggested Earth might drag ether locally, though this contradicted stellar aberration observations. The result was puzzling and unsatisfying. Many physicists initially dismissed the experiment, assuming some experimental error or overlooked effect explained the null result. But Michelson's reputation for experimental precision made wholesale dismissal difficult. The experiment was repeated numerous times with increasing precision. Morley and Dayton Miller repeated it in 1902 to 1904 using an improved apparatus with longer light paths. Still null. Miller continued experiments through the 1,920 seconds, eventually claiming a tiny positive result, but other physicists analyzing his data found systematic errors. In 1932, Roy Kennedy and Edward Thorndike performed a modified version, testing whether the two-way speed of light varied with time as Earth's velocity changed, still null. Every experiment attempting to detect the ether found nothing. Several explanations were proposed to save ether theory. The most prominent was Fitzgerald-Lorentz contraction. objects moving through ether contract along the direction of motion by a factor depending on velocity. The contraction factor equals the square root of the quantity 1 minus the velocity squared divided by light speed squared. At Earth's orbital velocity of 30 kilometers per second, this predicts contraction of about 1 part in 200 million. The interferometer's arm parallel to Earth's motion would contract by exactly the amount needed to cancel the expected time difference, producing the null result. But this explanation seemed contrived, inventing an effect specifically to explain why the experiment failed. Why should objects contract when moving through ether? What mechanism causes contraction? Fitzgerald and Lorentz proposed the contraction resulted from electromagnetic forces holding matter together being affected by motion through ether. Since electromagnetic forces propagate at light speed, motion through ether would alter the force balance, squeezing objects along the motion direction. This was more satisfying than pure ad hoc invention, but it felt like saving a theory against mounting contrary evidence. Time dilation added another layer. Lorentz showed that clocks moving through ether should run slow by the same factor as length contraction. A clock moving at velocity v through ether ticks at a rate equal to 1 minus the square root of 1 minus v squared over c squared times the rate of a stationary clock. For Earth's orbital velocity, clocks should lose about 1 second every 12 years. This effect, combined with length contraction, would perfectly cancel any observable effect of motion through ether in electromagnetic experiments. But again, this seemed like conspiracy, two separate effects precisely cancelling to hide the ether. Poincaré recognized that if nature conspires to make the ether undetectable, perhaps we should question whether ether exists. In 1900, he suggested the impossibility of detecting absolute motion might be a fundamental law of nature. By 1904, he was using Lorentz transformations and discussing how space and time coordinates mix. He came tantalizingly close to special relativity, but couldn't quite abandon the ether conceptually. His mathematics was correct, but his physical interpretation remained anchored to classical ideas: ether, absolute space, absolute time. Einstein, unaware of or unconcerned with most experimental details, approached the problem from pure principle. In 1905, he published On the Electrodynamics of Moving Bodies, now known as the Special Relativity paper. Einstein's approach was radical. He simply postulated that the speed of light is constant in all inertial reference frames, and that the laws of physics are the same in all inertial frames. From these two postulates, he derived the Lorentz transformations as logical necessities, not ad hoc fixes. Length contraction and time dilation weren't effects of motion through ether. They were consequences of space-time structure. The Michelson-Morley experiment is often cited as the key evidence prompting Einstein's theory, but Einstein later claimed he wasn't strongly influenced by it. He was aware of the null result, but based his theory primarily on the theoretical contradiction between Maxwell's equations and Galilean relativity. The experiment's importance lies more in later validation. It confirmed a key prediction of relativity, that light speed is independent of the observer's motion. The experiment designed to detect the ether instead disproved it, clearing the way for a revolutionary new understanding of space and time. Modern repetitions of Michelson-Morley using laser interferometers have achieved sensitivity billions of times better than the original experiment. These tests constrain any variation in light speed to less than 1 part in 10 to the 17th power, extraordinarily stringent limits. Every test confirms the null result. Light speed is constant, the ether doesn't exist, and space and time are not what Newton thought. The experiment that found nothing was actually finding everything, revealing that our intuitive understanding of space, time, and motion was fundamentally wrong and needed complete reconstruction. The Special Relativity paper that changed everything. On the 30th of June 1905, Albert Einstein submitted a paper titled Zur Elektrodynamik bewegter Körper on the electrodynamics of moving bodies to the German physics journal Annalende Physik. The paper appeared in print on the 26th of September 1905, occupying 30 pages in volume 17 of the journal. This paper, written by a 26-year-old patent clerk in Bern, Switzerland, revolutionized physics by abolishing absolute space and time and reconstructing mechanics from two simple postulates. Einstein worked essentially alone, without access to university facilities, discussing ideas with a few friends in an informal group they called the Olympia Academy. Yet he solved a problem that had baffled the leading physicists of his generation. The paper begins without references to prior work, no citations of Lorentz, Poincaré, Fitzgerald, or the Michelson-Morley experiment. Einstein starts from scratch, identifying a fundamental asymmetry in electromagnetic theory. When a magnet moves near a conductor, the magnet's magnetic field induces an electric field in the conductor's frame, producing current. When a conductor moves near a stationary magnet, the conductor moves through the magnetic field, and the Lorentz force on moving charges produces current. Same current, same observable result, but explained differently depending on which object is considered at rest. Einstein found this asymmetry unsatisfying. The physics shouldn't depend on arbitrary choice of reference frame. Einstein proposed two postulates as the foundation for a new mechanics. The first postulate, the principle of relativity, states that the laws of physics have the same form in all inertial reference frames. An inertial frame is one moving at constant velocity with no acceleration. The laws governing mechanics, electromagnetism, optics, and all other physical phenomena should be identical, whether you're stationary or moving at constant velocity. No experiment performed inside a closed laboratory can determine whether the lab is at rest or moving uniformly. This extended Galileo's relativity principle from mechanics to all physical laws. The second postulate, the light postulate, states that light travels at the same speed in all inertial frames, regardless of the source's motion. This speed, denoted c, is the same whether light comes from a moving star or a stationary lamp, measured by an observer at rest or an observer moving at high velocity. This postulate contradicted Galilean velocity addition and seemed paradoxical. How can light from a moving source have the same speed as light from a stationary source? Einstein accepted this apparent paradox as fundamental truth and showed that space and time must adjust to make it consistent. From these two postulates, Einstein derived profound consequences. If light speed is constant for all observers, then two observers moving relative to each other must disagree about time and space measurements. Events simultaneous in one frame occur at different times in another frame. Simultaneity is relative. Time intervals dilate, moving clocks run slow. Space intervals contract, moving objects shrink along their direction of motion. These aren't illusions or measurement artifacts, but genuine properties of spacetime, the four-dimensional combination of space and time that underlies physical reality. Einstein derived the Lorentz transformations as the mathematical expressions of how coordinates change between reference frames moving at constant relative velocity. If one observer uses coordinates x, y, z, t, and another observer moves at velocity v in the x direction, the second observer's coordinates relate to the first through the transformation. X prime equals gamma times the quantity x minus v times t, y prime equals y, z prime equals z, t prime equals gamma times the quantity t minus v times x divided by c squared. The factor gamma equals 1 divided by the square root of 1 minus v squared over c squared. This factor approaches infinity as velocity approaches light speed, making transformations increasingly dramatic. The paper contained no experimental section, no observational data, no graphs or photographs. It was pure theory developed from thought experiments, imagined scenarios involving clocks, light signals, and observers moving at different velocities. Einstein's most famous thought experiment involved a train moving at high velocity and lightning strikes hitting the front and back simultaneously in the train's frame. An observer on the ground sees the strike at the train's front occur before the strike at the back, because light from the front strike reaches the train's center later due to the train's motion. Simultaneity depends on reference frame, a revolutionary conclusion that violated all intuition. Einstein concluded the paper by deriving how velocities transform between frames. If an object moves at velocity u in one frame, and that frame moves at velocity v relative to another frame, the object's velocity in the second frame equals u plus v divided by 1 plus u times v divided by c squared. This relativistic velocity addition formula reduces to simple addition when velocities are small compared to light speed, recovering Galilean relativity at low speeds. But at high speeds, velocities don't simply add. If u and v both equal 0, 9c, their sum in classical mechanics would be 1, 8c faster than light. But the relativistic formula gives 0, 994c, still less than light speed. The paper's reception was initially muted. Einstein was an unknown patent clerk, not an established professor. The paper appeared among many others in Annalen der Physik without special fanfare. Some physicists read it and recognized its importance immediately, but widespread acceptance took years. Max Planck, editor of Annalen der Physik and already famous for his work on quantum theory, was one of the first supporters, discussing relativity in lectures and encouraging students to work on it. Gradually, physicists realized Einstein had resolved the contradictions between mechanics and electromagnetism that had troubled the field for decades. 3 months after the June 1905 paper, Einstein submitted a follow-up paper in September 1905 titled, "Does the inertia of a body depend upon its energy content?" This 3-page paper derived the most famous equation in physics, E equals mc squared. Einstein showed that mass and energy are equivalent, related by the conversion factor of light speed squared. An object's energy increases when it moves, and this energy increase manifests as a mass increase, relativistic mass. As velocity approaches light speed, energy and mass approach infinity, making light speed an unreachable barrier for massive objects. Einstein's theory explained why the Michelson-Morley experiment failed without invoking ad hoc length contraction. Length contraction emerged naturally from the Lorentz transformations as a consequence of space-time structure, not as a dynamical effect of motion through ether. Time dilation similarly emerged as a consequence rather than a hypothesis. The ether became unnecessary. Maxwell's equations worked perfectly without it, and electromagnetic waves propagated through empty space without requiring a medium. Space-time itself provided the stage for physics, and its structure determined the speed limit. The 1905 paper changed physics permanently, but Einstein's fame came later. He received his PhD in 1905, based on a different paper about molecular dimensions. He remained at the patent office until 1909, when he finally obtained an academic position. The Nobel Prize in 1921 honored his work on the photoelectric effect, not relativity, partly because relativity remained controversial. But by the 1920 seconds, special relativity was established beyond doubt, confirmed by numerous experiments and incorporated into the foundation of modern physics. The paper that questioned absolute space and time had demolished the classical worldview and replaced it with something stranger but more correct: the Lorentz transforms where space and time mix. The Lorentz transformations are the mathematical heart of special relativity, describing how space and time coordinates change between reference frames in relative motion. These equations, first derived by Hendrik Lorentz in 1892 and reinterpreted by Einstein in 1905, replace the Galilean transformations of classical mechanics. Where Galilean transformations keep time absolute and transform only space, Lorentz transformations mix space and time together in a velocity-dependent way. This mixing is the mathematical expression of relativity's central insight. Space and time are not separate entities, but aspects of a unified four-dimensional spacetime. The key to Lorentz transformations is the Lorentz factor, universally denoted by the Greek letter gamma. This factor equals 1 divided by the square root of the quantity 1 minus v squared divided by c squared, where v is the relative velocity between frames and c is light speed. At low velocities much less than light speed, v squared over c squared is negligibly small, making gamma approximately equal to 1. The transformations reduce to Galilean transformations and relativistic effects vanish. But as velocity approaches light speed, gamma grows rapidly, approaching infinity as v approaches c. At velocity equal to half light speed 0, 5c, or about 150,000 kilometers per second, the Lorentz factor gamma equals 1.15. Relativistic effects are noticeable but modest. Moving clocks run 15% slow. Moving lengths contract by 15%. At 0866c, approximately 87% of light speed, or 260,000 kilometers per second, gamma equals 2. Time dilates by a factor of 2. 1 hour on a moving clock corresponds to 2 hours on a stationary clock. Lengths contract by half. A meter stick moving at 866c measures only 0.5 meters long in the stationary frame. At 09c, gamma equals 2.29. At 099c, gamma jumps to 7.09. At 0999c, gamma reaches 22.4. The growth is exponential, accelerating as velocity approaches light speed. At 09,999c, 99.99% of light speed gamma equals 70.7. At 09999c, gamma reaches 224. At 6,9,09999c, gamma equals 707. Every additional 9 roughly multiplies gamma by the square root of 10, or about 3.16. This exponential growth makes reaching light speed impossible because relativistic mass, which equals gamma times rest mass, would become infinite. The Lorentz transformation for time includes a term mixing space and time. T prime equals gamma times the quantity t minus vx over c squared. This mixing term, vx over c squared, depends on both velocity and position. Events at different locations can have their time order reversed, depending on reference frame. If two events occur simultaneously at different positions in one frame the same time t, but different x, they occur at different times in a moving frame because the vx term differs. Simultaneity is relative. Whether two separated events happen at the same time depends on who's measuring. Length contraction follows directly from the Lorentz transformations. A rod of proper length L, its length in its rest frame, has length L divided by gamma in a frame where it moves at velocity v. The contraction occurs only along the direction of motion. A rod oriented perpendicular to the motion doesn't contract. A meter stick moving at 9c measures 0.44 meters in the stationary frame. At 099c, it measures 0.14 meters. At 0999c, it measures just 0.045 meters less than 5 centimeters. The stick isn't compressed by any force. Its proper length remains 1 meter in its rest frame. The contraction is a consequence of space-time geometry. Time dilation is the most dramatic relativistic effect. A clock moving at velocity v ticks at a rate 1 over gamma compared to a stationary clock. The moving clock runs slow, fewer ticks occur in a given time interval. measured by the stationary clock. A clock moving at 0.9c runs at 44% of normal rate. At 0.99c, it runs at 14%. At 0.999c, only 4.5%. If a spaceship travels at 0.999c, for what its clock measures as 1 year, more than 22 years pass on Earth. The effect is symmetric from the spaceship's perspective. Earth clocks run slow. This seems paradoxical, but resolves because comparing clocks requires acceleration to bring them back together, breaking the symmetry. The relativistic velocity addition formula prevents velocities from exceeding light speed. If object A moves at velocity u relative to object B, and B moves at velocity v relative to object C, then A moves at velocity u plus v divided by 1 plus u times v over c squared relative to c. This formula ensures that if both u and v are less than c, the combined velocity is also less than c. For example, if u equals 0, 9c, and v equals 0, 9c, classical addition gives 1, 8c. But the relativistic formula gives 0, 9c plus 0, 9c divided by 1 plus 0.81, which equals 1, 8c divided by 1.81, which equals 0, 994c, still under the light speed limit. This velocity addition formula has been tested extensively in particle accelerators. When protons already moving at 0.9c are accelerated further, their velocity increases but remains below c. Adding energy doesn't keep increasing velocity proportionally as Newton's mechanics predicts. Instead, the energy goes into increasing relativistic mass. The Large Hadron Collider accelerates protons to 0.9999991c, gamma equals 7,460. Adding more energy increases gamma, but barely changes velocity, going from 0.9999991c to 0.999999995c doubles the energy, but increases velocity by only 0.000000004c. The Lorentz transformations preserve the space-time interval between events. In classical mechanics, all observers agree on spatial distances and time intervals separately. In relativity, observers disagree about spatial distances and time intervals individually, but they agree on a combined quantity. The interval, the space-time interval, equals c squared times the time difference squared minus the spatial separation squared. This interval is the same in all inertial frames and invariant quantity. Events with zero interval are separated by light travel. Light emitted at one event reaches the other event. Events with positive interval are time-like separated. Signals can travel between them slower than light. Events with negative interval are space-like separated. No signal can connect them without exceeding light speed. Hermann Minkowski, Einstein's former mathematics professor, reformulated special relativity in 1908 using four-dimensional space-time geometry. Minkowski showed that space and time aren't separate, but form a four-dimensional continuum where the Lorentz transformations represent rotations. Just as rotating your viewpoint in three-dimensional space mixes x, y, and z coordinates, changing reference frame in four-dimensional space-time mixes space and time coordinates. The Lorentz transformations are rotations in space-time, with the rotation angle related to velocity. Light speed is the conversion factor between space and time units, analogous to how one might convert between meters and seconds. The mathematics of Lorentz transformations seemed bizarre when first encountered, contradicting all intuition built from everyday low-speed experience, but they're mathematically elegant and internally consistent. They reduce to Galilean transformations at low speeds, preserving Newtonian mechanics in its domain of validity. They automatically preserve Maxwell's equations. Electric and magnetic fields transform in specific ways that maintain the equation's form. They predict bizarre phenomena time dilation, length contraction, relativity of simultaneity, all confirmed by experiment. The transformations aren't approximations or corrections to classical mechanics, but rather the exact description of how space-time actually works. The equals mc squared that made mass and energy one. On the 27th of September 1905, 3 months after publishing his special relativity paper, Einstein submitted a short 3-page follow-up paper titled Ist die Trägheit eines Körpers von seinem Energiegehalt abhängig? Does the inertia of a body depend upon its energy content? This brief paper derived the most famous equation in physics, E equals mc squared. Einstein showed that mass and energy are equivalent, two forms of the same thing related by the square of light speed. This equivalence revolutionized physics, explaining nuclear energy, antimatter, and why nothing with mass can reach light speed. Einstein's derivation considered a body emitting 2 pulses of light in opposite directions. From the body's rest frame, it emits equal energy in each direction and remains at rest, no net momentum change. From a moving frame, the body also remains at rest in its own frame, but the emitted light carries momentum. By conservation of energy and momentum, the body's mass must decrease when it emits electromagnetic radiation. The energy emitted equals the mass lost times c squared. This established the principle: energy has mass, and mass is a form of energy. The equation E equals mc squared applies to rest mass, the mass of an object in its rest frame. This rest energy represents the energy equivalent of the object's mass, available in principle if the mass could be completely converted to other forms of energy. For 1 kilogram of mass, the rest energy equals 1 kilogram times 299,792,458 meters per second squared, which equals about 9 times 10 to the 16th joules. This is roughly 21 megatons of TNT, equivalent more than the largest nuclear weapon ever tested. Mass contains enormous energy, though extracting it remains challenging. Nuclear reactions convert small fractions of mass to energy. In nuclear fission, uranium-2, 3, 5 nuclei split into lighter fragments with total mass about 0.1% less than the original nucleus. This missing mass, called the mass defect, appears as kinetic energy of the fragments and radiation. The Hiroshima atomic bomb converted roughly 700 milligrams of matter to energy, releasing about 15 kilotons of TNT equivalent. In nuclear fusion, hydrogen nuclei combine to form helium with 0.7% mass loss. The Sun converts 4 million tons of mass to energy every second through fusion, losing mass at this enormous rate, yet containing enough fuel for another 5 billion years. Antimatter provides the ultimate mass-energy conversion. When matter meets antimatter, they annihilate completely, converting 100% of their combined mass to energy, mostly photons. 1 kilogram of matter plus 1 kilogram of antimatter would yield 180 million terajoules, far exceeding any chemical or nuclear reaction. But antimatter doesn't exist naturally on Earth in significant quantities. It must be created in particle accelerators at enormous energy cost, making it useless as an energy source. Still, antimatter's theoretical perfection as fuel drives its prominence in science fiction. For moving objects, total energy includes both rest energy and kinetic energy. The total energy equals gamma times rest mass times c squared, where gamma is the Lorentz factor. Kinetic energy, energy of motion, equals the quantity gamma minus 1 times rest mass times c squared. At low speeds, where gamma approximately equals 1 plus 1/2 v squared over c squared, this reduces to the classical formula 1/2 m times v squared. But at high speeds, kinetic energy grows much faster than classically, approaching infinity as velocity approaches light speed. At velocity equal to 0, 5c, gamma equals 1.15, so kinetic energy equals 0.15 times rest energy, 15% of mc squared. At 0866c, gamma equals 2. So, kinetic energy equals rest energy. The object has as much energy in motion as in its rest mass. At 09c, kinetic energy equals 1.29 times rest energy. At 099c, kinetic energy equals 6.09 times rest energy. At 0999c, kinetic energy equals 21.4 times rest energy. Each order of magnitude closer to light speed roughly multiplies the required energy by a factor of 3. This exponential growth in required energy makes light speed unreachable for massive objects. To accelerate 1 kilogram from 09c to 99c requires adding kinetic energy equal to about 4.8 times rest energy, or 4.3 times 10 to the 17th joules, to go from 99c to 999c requires adding another 15.3 times rest energy, or 1.4 times 10 to the 18th joules. Each factor of 10 closer to light speed requires roughly 10 times more energy. Reaching exactly light speed would require infinite energy, a physically impossible condition. Light speed is an asymptotic limit, approachable but never reachable by anything with mass. The equation also explains why photons have no mass. Photons always travel at exactly light speed, never faster or slower. If photons had any mass, their energy would be infinite, because gamma is infinite at v equals c. Since photons clearly have finite energy proportional to their frequency, they must have exactly zero rest mass. The same applies to other force-carrying particles like gluons. Particles with mass can never reach light speed. Particles without mass must always travel at exactly light speed. There's no middle ground. Relativistic mass increase has been measured directly in particle accelerators for over a century. When electrons accelerate through electric fields, their trajectories bend in magnetic fields according to their momentum. At low speeds, momentum equals mass times velocity, so deflection depends on velocity. But at high speeds, electrons deflect less than classical mechanics predicts, because their relativistic mass increases, increasing momentum beyond the classical value. Measurements perfectly match the prediction that relativistic mass equals gamma times rest mass. The equivalence of mass and energy has profound implications for cosmology. The universe's total energy, including the energy of all matter mass times c squared, might be exactly zero if we account for gravitational potential energy as negative. Matter has positive energy, but gravitational attraction between matter creates negative potential energy. If these exactly balance, the universe could emerge from quantum fluctuations without violating energy conservation. The total energy is zero. Positive mass energy cancels negative gravitational potential energy, making the universe the ultimate free lunch. Mass energy equivalence also constrains particle physics. When particles collide at high energy, new particles can be created from the kinetic energy of collision. The Large Hadron Collider accelerates protons to 6.5 trillion electron volts each. When two protons collide head-on, their combined kinetic energy, 13 trillion electron volts, can produce particles with masses up to about 13 TeV divided by c squared. The Higgs boson, discovered in 2012, has mass 125 GeV divided by c squared. Creating it required collisions with sufficient energy to materialize this mass from pure kinetic energy. The equation E equals mc squared is often misunderstood as applying only to nuclear reactions or antimatter. Actually, it applies to all mass and all energy. A compressed spring has slightly more mass than an uncompressed spring, because compression stores potential energy, and that energy has mass. A hot object has slightly more mass than when cold, because thermal energy contributes to mass. A spinning flywheel has more mass than when stationary. These differences are typically negligible, far too small to measure, but they're real. Every joule of energy adds 1/c² kilograms of mass, about 10 to the -17th kilograms per joule. Einstein's 3-page paper derived the most famous equation from simple considerations about light emission and energy conservation. The paper contained no experimental data, no mathematical complexity beyond algebra, yet it changed our understanding of reality's fundamental nature. Mass is concentrated energy. Energy is dispersed mass. They're interconvertible, related by the fastest speed in the universe squared. This relationship explains the sun's power, nuclear weapons' destructiveness, why particle accelerators can't reach light speed, and why the universe's speed limit is so absolute. Nothing with mass can reach light speed, because doing so would require infinite energy, a physical impossibility, embedded in space-time structure, the momentum increase that makes acceleration harder. In classical mechanics, momentum equals mass times velocity p equals m times v. Momentum is a conserved quantity, meaning the total momentum of an isolated system never changes. When you apply force to an object, Newton's second law states that force equals the rate of change of momentum, F equals dp over dt. For constant mass, this reduces to the familiar F equals ma, force equals mass times acceleration. Apply constant force and the object accelerates uniformly, gaining velocity at a constant rate. This works perfectly at everyday speeds, but fails completely near light speed. In special relativity, momentum must be redefined to preserve conservation laws. Relativistic momentum equals gamma times mass times velocity, p equals gamma times m times v, where gamma is the Lorentz factor. At low speeds, where gamma approximately equals 1, this reduces to classical momentum. But at high speeds, gamma grows large, dramatically increasing momentum beyond the classical value. An object moving at 0.9c has momentum 2.29 times greater than classical momentum. At 0.999c, momentum is 4 times greater. As velocity approaches light speed, momentum approaches infinity despite velocity approaching a finite limit. Newton's second law, F equals dp over dt, still holds in relativity, but dp over dt behaves differently. When you apply constant force to an object initially at rest, the object accelerates. But as velocity increases, gamma increases, and momentum grows faster than velocity. The same force produces less and less acceleration because momentum increases require both velocity increase and gamma increase. At first, acceleration is nearly constant, gamma is close to 1. But as velocity approaches light speed, acceleration drops towards 0. Constant force produces ever smaller velocity increments, approaching 0 increase as v approaches c. This can be expressed mathematically. The acceleration equals force divided by gamma cubed times mass. The gamma cubed factor emerges from taking the derivative of gamma times velocity with respect to time. At low speeds, where gamma equals 1, acceleration equals force over mass classical mechanics. At 0.9c, where gamma equals 2.29, acceleration is 12 times smaller than classical prediction for the same force. At 0.99c, where gamma equals 7.09, acceleration is 356 times smaller. At 0.999c, where gamma equals 22.4, acceleration is 11,200 times smaller. Each order of magnitude closer to light speed decreases acceleration by roughly another factor of 30. Particle accelerators demonstrate this daily. The Large Hadron Collider accelerates protons to 0.9999991c, corresponding to gamma equal to 7,460. At this speed, applying the same force, that initially accelerated protons produces acceleration about 4 times 10 to the 11th times smaller than at low speed. The protons barely speed up at all despite enormous energy input. Essentially, all the energy goes into increasing relativistic mass, the gamma factor, rather than velocity. Engineers designing the LHC accounted for this, using 16.7 million electron volts to increase proton energy from 7 to 7.5 tera electron volts, while changing velocity by only 0.000000004 c. The Stanford Linear Accelerator, which operated from 1966 to 2008, accelerated electrons through a 2-mile-long tube to energies of 50 giga-electron volts. At this energy, electrons reach velocity 0.9999995 c gamma equals 100,000. The electrons travel the accelerator's length in about 22 microseconds, measured in the lab frame, but only 0.2 microseconds measured in the electron's frame due to time dilation. Despite enormous energy, 50 GeV, compared to the electron's rest energy of 0.511 MeV velocity, changed by only 0.0000000000005 c from the initial 999 c. Almost all energy increased gamma. Why does momentum increase this way? The reason lies in preserving conservation laws across reference frames. In classical mechanics, momentum is conserved in all inertial frames using Galilean transformations. In relativity, for momentum to remain conserved in all frames using Lorentz transformations, momentum must equal gamma times mass times velocity. Any other definition would violate momentum conservation when transforming between frames. Einstein derived relativistic momentum by requiring this conservation, showing it's a logical necessity rather than an empirical correction. The momentum formula connects to energy through the energy-momentum relation. Total energy squared equals rest energy squared plus momentum times c squared. Written as an equation, E squared equals the quantity mc squared squared plus the quantity pc squared. For objects at rest where momentum equals 0, this reduces to E equals mc squared. For objects in motion, energy includes both rest energy and kinetic energy, and momentum relates to kinetic energy through this equation. For photons with 0 mass, energy equals momentum times c. All energy is kinetic, none is rest energy. The increasing difficulty of acceleration explains why rockets can't reach light speed through conventional propulsion. A rocket accelerating by expelling mass, the only way to accelerate in space without external forces, faces exponentially worsening efficiency. The rocket equation in classical mechanics states that final velocity depends logarithmically on the mass ratio. But in relativity, even an ideal rocket with perfect efficiency and infinite fuel can't exceed light speed. As the rocket approaches c, exponentially more fuel is required for each incremental velocity gain, and the rocket's frame-dilated time means less proper time passes on board for a given distance traveled. Cosmic rays provide natural examples of relativistic momentum. Cosmic ray protons striking Earth's atmosphere have energies up to 10 to the 20th electron volts, 100 billion times more than LHC protons. At this energy, gamma equals about 10 to the 11th 100 billion. Velocity differs from light speed by only 1 part in 10 to the 22nd. Yet momentum continues increasing linearly with energy, even though velocity has essentially stopped changing. These particles have momentum equal to their energy divided by c, acting almost like massless particles, despite having proton mass. The momentum increase makes collisions between relativistic particles particularly energetic. When a cosmic ray proton at 10 to the 20th electron volts collides with an atmospheric nucleus, the collision energy available in the center of mass frame is enormous enough to create showers of hundreds or thousands of secondary particles cascading through the atmosphere. These extensive air showers can be detected at ground level through Cherenkov light, and particle detectors spread over square kilometers. The highest energy cosmic ray ever detected, the Oh My God particle in 1991, had energy 3 times 10 to the 20th electron volts, equivalent to a baseball traveling at 100 kilometers per hour, concentrated in a single proton. The relativistic momentum formula has been tested in countless particle physics experiments over more than a century. Every measurement confirms that momentum equals gamma times mass times velocity. When particles scatter in collisions, momentum conservation holds precisely using this formula. The standard model of particle physics, the most precisely tested theory in science, relies fundamentally on relativistic momentum in calculating scattering amplitudes, decay rates, and cross-sections. The theory works because momentum increases with gamma, not despite it. From a practical standpoint, the momentum increase means that accelerating spacecraft to even moderate relativistic speeds requires impractical amounts of energy. Accelerating a 1,000 kilogram spacecraft to 0, 1c requires kinetic energy equal to 1/2 times 1,000 kilograms times 0. 1c squared, approximately 4.5 times 10 to the 14th joules, or about 100 kilotons of TNT equivalent. To reach 0, 9c requires 1.3 times 10 to the 18th joules, about 300 megatons. To reach 0, 99c requires 5 times 10 to the 18th joules. Each order of magnitude closer to light speed roughly multiplies required energy by a factor of 3. Reaching light speed requires infinite energy, an insurmountable barrier built into space-time structure. The particle accelerators that prove Einstein right, the Large Hadron Collider, operated by CERN near Geneva, Switzerland, accelerates protons to 99.99999% of light speed, a velocity of 299,792,455 meters per second, only 3 meters per second slower than light. At this speed, the Lorentz factor gamma equals 7,460, meaning each proton has relativistic mass 7,460 times its rest mass. The protons carry kinetic energy of 6.5 trillion electron volts, or 6.5 TeV, compared to rest energy of only 938 million electron volts. More than 99.99% of the proton's energy is kinetic, energy of motion, yet velocity differs from light speed by less than 1 part in 100 million. The LHC consists of a ring 27 kilometers in circumference, buried 100 meters underground. Protons circle this ring 11,245 times per second, completing each lap in 89 microseconds. Over the course of acceleration from injection energy to maximum energy, protons gain 6.5 TeV, while velocity increases by only about 3 meters per second from 299,792,452 to 299,792,455 meters per second. Essentially, all the energy goes into increasing the gamma factor rather than velocity. This demonstrates directly that energy and mass are equivalent, not that energy increases velocity indefinitely, as classical mechanics would predict. The LHC uses superconducting magnets to bend the proton beam around the circular path. The required magnetic field strength depends on the beam's momentum. At 6.5 TeV, proton momentum equals 6.5 TeV divided by c, or about 3.5 times 10 to the minus 15th kilogram meters per second, 7,460 times greater than classical momentum at the same velocity. The dipole magnets produce fields of 8.3 Tesla, roughly 160,000 times Earth's magnetic field, to bend this enormous momentum around the ring. Without relativistic mass increase, magnets 7,460 times weaker would suffice 0.001 Tesla, barely stronger than Earth's field. When proton beams collide in the LHC, the total energy in the center of mass frame reaches 13 TeV. This energy can materialize into new particles through E equals mc squared. The Higgs boson, discovered at the LHC in 2012, has mass equivalent to 125 GeV. Creating Higgs bosons requires collisions with at least 125 GeV available energy, easily achieved by the LHC's 13 TeV collisions. The Higgs appears in only about 1 collision in 10 billion, because creating massive particles from kinetic energy is probabilistic, requiring the right quantum configuration. But when collisions do create Higgs bosons, they demonstrate mass energy equivalence directly. The Stanford Linear Accelerator Center, now SLAC National Accelerator Laboratory, operated a 2-mile-long linear accelerator from 1966 to 2008. This machine accelerated electrons to energies up to 50 GeV, corresponding to gamma equal to 100,000. At this gamma factor, velocity equals 0.999999995 c, differing from light speed by only 0.00000000005 c, or about 15 centimeters per second. An electron traveling at this velocity would circle Earth in 0.13 seconds, yet it's still slower than light, which would circle Earth in 0.13 seconds minus 0.00000000018 seconds. Time dilation at gamma equals 100,000 means that 1 second in the lab frame corresponds to only 0.00001 seconds, 10 microseconds, in the electron's rest frame. The 2-mile accelerator appears contracted to only 100 feet in the electron's frame. From the electron's perspective, it traverses this contracted distance in 0.33 microseconds. From the lab perspective, the electron takes 33 microseconds to traverse 2 miles. Both perspectives agree on physics but measure different times and distances, related by the Lorentz transformations. Muons produced by cosmic rays provide a natural demonstration of time dilation. Muons are unstable particles similar to heavy electrons, with rest mass 105.7 MeV divided by c squared and mean lifetime 2.2 microseconds in their rest frame. Cosmic ray protons striking the upper atmosphere at altitudes around 15 kilometers produce showers of particles, including muons. These muons travel downward at speeds very close to light speed, typically 9,999 c or faster. At 9,999 c, gamma equals 70.7, so time dilates by a factor of 70.7. Muons live 155 microseconds in the lab frame instead of 2.2 microseconds. Without time dilation, muons traveling at 9,999 c would travel only about 660 meters before decaying. Most would decay high in the atmosphere and never reach ground level. But observations show abundant muons at sea level, with fluxes of about 1 muon per square centimeter per minute. This excess of muons proves time dilation. In the lab frame, muons live longer due to time dilation. From the muon's perspective, its lifetime remains 2.2 microseconds, but the distance to the ground appears contracted by gamma equal to 70.7, reducing 15 kilometers to 212 meters. Either perspective explains why muons reach the ground, demonstrating the consistency of relativistic transformations. Bruno Rossi and David Hall performed quantitative measurements of muon time dilation in 1941. They measured muon fluxes at the top of Mount Washington in New Hampshire at altitude 1,907 meters and at sea level in Cambridge, Massachusetts. The flux ratio, combined with measured muon speeds and the altitude difference, allowed calculation of muon lifetime in the lab frame. Results showed time dilation factor consistent with special relativity. Subsequent experiments have measured muon lifetimes at various energies, always finding agreement with gamma times rest lifetime. The relativistic heavy ion collider at Brookhaven National Laboratory accelerates gold nuclei atoms with 79 protons and 118 neutrons to energies of 100 GeV per nucleon. These nuclei reach velocities of 0.99995 c, corresponding to gamma equal to 100 per nucleon. At this velocity, each gold nucleus has relativistic mass 19,700 times its rest mass. The nuclei collide head-on, creating a quark-gluon plasma where protons and neutrons melt into their constituent quarks and gluons at temperatures exceeding 2 trillion degrees Kelvin, 100,000 times hotter than the Sun's core. The Tevatron at Fermilab, which operated from 1983 to 2011, accelerated protons and antiprotons to 980 GeV 0.98 TeV, corresponding to velocity 0.99996 c, and gamma equal to 1045. When proton and antiproton beams collided, the total center of mass energy reached 1.96 TeV. The Tevatron discovered the top quark in 1995, a particle with mass 173 GeV divided by c squared 185 times heavier than a proton. Creating top quarks required collisions energetic enough to materialize 173 GeV worth of mass, demonstrating E equals mc squared in particle creation. Synchrotron radiation provides another relativistic effect visible in particle accelerators. When charged particles accelerate, including centripetal acceleration from circular motion, they emit electromagnetic radiation. The radiated power increases as gamma to the fourth power, making synchrotron radiation negligible at low speeds but dominant at high speeds. In the LHC, each proton radiates about 7,900 electron volts per turn due to synchrotron radiation. This energy loss must be compensated by radio frequency cavities that add energy back to the beam. The strong gamma dependence of synchrotron radiation makes circular electron accelerators impractical at very high energies, favoring linear designs like SLAC. The mass increase measured in particle accelerators isn't just theoretical, it affects beam dynamics and must be accounted for in accelerator design. The Betatron oscillation frequency, the rate at which particles oscillate transversely around the ideal orbit, depends on relativistic mass. As particles accelerate and gamma increases, oscillation frequency decreases. Engineers design accelerator lattices to maintain stable oscillations across the entire energy range. Incorrect treatment of relativistic mass would cause beam instability and loss. The fact that accelerators work as designed proves relativity is correct. Modern particle accelerators achieve energies and velocities that would have seemed impossible a century ago. The LHC reaches energies 7,000 times greater than the first cyclotron built by Ernest Lawrence in 1932, which accelerated protons to 80,000 electron volts. Yet velocity has increased only from 6% of light speed to 99,999,999, 1%, a factor of 17. The vast energy increase produces only modest velocity increase, because relativistic mass grows exponentially near light speed. This exponential growth makes light speed an asymptotic barrier, approachable but unreachable, regardless of how much energy is available. The time dilation measured in atomic clocks. In October 1971, Joseph Hafele and Richard Keating performed an experiment that directly measured time dilation predicted by special relativity. They flew 4 cesium beam atomic clocks around the world, twice once eastward and once westward, on commercial airline flights. Upon return, they compared the travelled clocks to reference clocks that remained at the United States Naval Observatory in Washington, D.C. The eastward traveling clocks lost 59 nanoseconds plus or minus 10 nanoseconds compared to ground clocks. The westward traveling clocks gained 273 nanoseconds plus or minus 7 nanoseconds. Both results matched predictions from special and general relativity within experimental uncertainty. The asymmetry between eastward and westward flights arises from Earth's rotation. Earth's surface, at the latitude of the flights roughly 30 to 40 degrees north, moves eastward at about 360 meters per second due to planetary rotation. An eastward flying plane adds its velocity to Earth's rotation, reaching about 600 meters per second relative to Earth's non-rotating center. A westward flying plane subtracts its velocity, reaching only about 120 meters per second relative to the center. Special relativity time dilation depends on velocity relative to an inertial frame approximately Earth's non-rotating center, so eastward flights experience more time dilation than westward flights. The calculation involves both special and general relativistic effects. Special relativity predicts that moving clocks run slow by factor 1 over gamma. For eastward flights averaging 600 meters per second, gamma equals approximately 1.000000000002, so clocks run slow by 2 parts in 10 to the 12th. Over flight time of about 50 hours, this produces about 180 nanoseconds of time loss. For westward flights at 120 meters per second, gamma is much closer to 1, producing only about 10 nanoseconds of time loss. But this accounts for only part of the effect. General relativity adds gravitational time dilation. Clocks at higher altitude experience weaker gravity and run faster than clocks at sea level. The effect equals the gravitational potential difference divided by c squared. At typical cruising altitude of 10 kilometers, gravitational potential is about 100,000 joules per kilogram, higher than at sea level. This makes clocks run fast by about 1 part in 10 to the 12th, very similar magnitude to the special relativistic slowing. Over 50 hours, this produces about 150 nanoseconds of time gain. For eastward flights, gravitational speed-up partly cancels kinematic slowing, yielding net loss of 59 nanoseconds. For westward flights, both effects add, yielding net gain of 273 nanoseconds. Hafele and Keating used 4 cesium beam atomic clocks, manufactured by Hewlett-Packard, model HP 5061A. These clocks kept time by measuring the microwave frequency of cesium-133 atomic transitions, stable to about 1 part in 10 to the 13th. The clocks flew in passenger cabins of commercial flights Pan Am, TWA, and other airlines with Hafele or Keating accompanying them. The experimenters logged flight times, altitudes, and speeds to calculate predicted time differences. The measured differences matched predictions within combined uncertainties from both theory and clock stability. The Global Positioning System provides continuous confirmation of time dilation. GPS satellites orbit at altitude 20,200 kilometers, moving at 3,874 meters per second. At this velocity, special relativity predicts satellite clocks run slow by about 7 microseconds per day. Velocity is small compared to light speed, so gamma equals 1 plus 8 times 10 to the minus 11th. But at their altitude, gravitational time dilation makes clocks run fast by about 45 microseconds per day. Gravitational potential is much higher than at Earth's surface, so this effect dominates. The net effect is that satellite clocks run fast by 38 microseconds per day compared to ground clocks. If GPS didn't account for relativity, position errors would accumulate at about 10 kilometers per day, 30 feet per second. After 1 day, GPS would be off by 10 kilometers. After 1 week, off by 70 kilometers, the system would be useless for navigation. GPS accounts for relativity by adjusting satellite clock frequencies before launch. The clocks are set to tick at 10.229999954 MHz, about 0.0045% slow, so that after relativistic effects, they tick at exactly 10.23 MHz as measured on the ground. This adjustment is permanent and automatic, not requiring any relativistic calculations by GPS receivers. Gravity Probe A, launched in 1976, provided another precision test of time dilation. The experiment flew a hydrogen maser clock to altitude 10,000 kilometers on a suborbital rocket flight. During the 2-hour flight, the clock experienced both special relativistic slowing due to velocity and general relativistic speeding due to altitude. Comparing the rocket clock's frequency to ground clocks via radio link measured the combined effect. Results matched relativity predictions to 70 parts per million, limited by clock stability and measurement uncertainty. The experiment confirmed that relativity works at altitudes far beyond normal aircraft flight. International Atomic Time, maintained by the Bureau International des Poids et Mesures in France, must account for relativistic effects when combining data from atomic clocks at different locations worldwide. Clocks at different altitudes run at different rates due to gravitational time dilation. Clocks at different latitudes also differ due to Earth's rotation, giving them different velocities. To define a common timescale, all clocks must be corrected to a standard geoid, essentially mean sea level. These corrections, typically tens of nanoseconds per day, are essential for maintaining time accuracy of 1 part in 10 to the 16th required for modern timekeeping. Particle accelerators provide even more dramatic time dilation. Muons created in the LHC have gamma factors reaching 100 or more, meaning their lifetime extends by factor of 100. A muon with 2.2 microsecond rest lifetime lives 220 microseconds in the lab frame at gamma equals 100. This extended lifetime allows muons to travel farther in detectors before decaying, and the measured travel distance directly measures time dilation. Detectors see muons decaying farther from their production point than would be possible without time dilation, confirming the effect at much larger gamma than achievable with clocks. Ives and Stilwell performed an early test of time dilation in 1938 using the Doppler shift of light from moving atoms. They observed hydrogen atoms in a discharge tube moving at several hundred kilometers per second. According to classical Doppler shift, light frequency should shift by v over c when the source moves, but relativistic Doppler shift includes an additional factor of 1 over gamma due to time dilation. By measuring the Doppler shift precisely, Ives and Stilwell detected the time dilation term, confirming relativity at velocities around 0, 1c much slower than modern accelerators, but fast enough for measurable effects. Mössbauer spectroscopy provides exquisitely sensitive tests of time dilation at low velocities. The Mössbauer effect allows measurement of photon energy shifts of 1 part in 10 to the 15th using nuclear transitions in iron 57. Placing a radioactive source on a rotating disk and detector at the disk's center, or vice versa, creates a velocity difference of perhaps 10 meters per second. The resulting time dilation gamma equals 1 plus 5 times 10 to the minus 16th, shifts photon energy by 1 part in 10 to the 15th, barely detectable but measurable. Results match relativity, confirming time dilation even at everyday velocities like walking speed. The consistency of all these tests, from aircraft flying at 200 meters per second to particles moving at 0, 9,999 C, demonstrates that time dilation is real, not an artifact or illusion. Moving clocks genuinely run slow, moving particles genuinely live longer, and the effect follows precisely the formula predicted by special relativity. Proper time equals coordinate time divided by gamma. This effect is now routine in particle physics and precision timekeeping, incorporated into every calculation and measurement. Time dilation is as established as any fact in physics, confirmed by millions of measurements over 8 decades. The length contraction nobody can directly see. Length contraction states that objects moving relative to an observer are shortened along the direction of motion by the Lorentz factor gamma. A meter stick moving at velocity v has length 1 meter in its rest frame, but length 1 divided by gamma meters in the observer's frame. At 0, 866 c, where gamma equals 2, the meter stick measures 0.5 meters. At 0.9 c, it measures 0.44 meters. At 0.99 c, it measures 0.14 meters. At 0.999 c, it measures 0.045 meters. As velocity approaches light speed, length approaches 0, though it never quite reaches 0 because velocity never quite reaches c. Unlike time dilation, which can be measured by comparing a traveling clock to a stationary clock after the journey, length contraction cannot be directly observed. The reason is fundamental. To measure an object's length, you must determine the positions of both ends simultaneously in your reference frame. But simultaneity is relative events simultaneous in one frame occur at different times in another. The very act of measuring length requires choosing a reference frame, and in that frame, the object's length is what relativity predicts. There's no frame-independent way to compare moving length to rest length because length itself is frame-dependent. However, length contraction has indirect confirmation. Muons created by cosmic rays in the upper atmosphere reach ground level in greater numbers than possible if the atmosphere's thickness were uncontracted. From the muon's perspective, its lifetime is 2.2 microseconds, too short to traverse 15 kilometers even at nearly light speed. But in the muon's frame, the atmosphere is contracted to perhaps 200 meters due to the muon's high velocity. The muon can traverse this contracted distance in 2.2 microseconds. The fact that muons reach the ground confirms that length contraction occurs in the muon's frame, complementing the time dilation explanation from Earth's frame. Particle accelerators provide quantitative evidence through beam dynamics. At the LHC, proton bunches are about 8 centimeters long in the lab frame, but only about 1 millimeter long in their rest frame. The contraction factor of 80 corresponds to gamma equal to 80, consistent with velocity around 0.99992 c. If length contraction didn't occur, the bunch would be 8 centimeters in all frames, and the collision dynamics would differ dramatically. The fact that bunch lengths measured in the lab frame match predictions that include length contraction validates the effect. Relativistic heavy ion collisions at RHIC demonstrate length contraction dramatically. Gold nuclei at gamma equal to 100 are contracted by factor of 100 along their direction of motion. In the nucleus's rest frame, the nucleus is spherical with diameter about 14 femtometers, 14 times 10 to the minus 15th meters. In the lab frame, the nucleus is a flattened disk only 0.14 femtometers thick, but still 14 femtometers wide, perpendicular to motion. When two such contracted nuclei collide head-on, they pass through each other in about 0.001 yoctoseconds 10 to the minus 27th seconds, creating a quark-gluon plasma in their wake. The contracted nuclei in RHIC collisions don't just pass through each other. Their collision creates thousands of particles as their kinetic energy converts to matter. The collision dynamics depend critically on the nuclei's contracted shape. Calculations treating the nuclei as spherical rather than contracted disks give wrong predictions for particle production patterns. The agreement between predictions using length-contracted nuclei and observed particle distributions confirms that length contraction occurs as relativity predicts, affecting physical processes in measurable ways. Thomas precession provides an indirect test of length contraction combined with other relativistic effects. When an object accelerates, changing velocity direction without changing speed magnitude, its orientation rotates in a frame-dependent way due to the non-commutativity of non-collinear Lorentz boosts. This precession affects the spin of particles orbiting in accelerators. Electrons orbiting in storage rings precess at a rate depending on velocity and energy. Measurements match predictions from relativity, including length contraction effects. Any deviation would show up as anomalous precession, but none is observed. Bell's spaceship paradox illustrates length contraction's reality. Imagine two spaceships initially at rest, separated by distance L, connected by a string. Both ships accelerate identically in the lab frame, maintaining constant separation L. In the lab frame, the string length remains L. But in the ship's frame, an accelerating non-inertial frame, the distance between ships appears to increase because of relativity of simultaneity and length contraction. The string must stretch and eventually breaks. This thought experiment shows length contraction has real physical consequences, not just measurement artifacts. Terral rotation complicates visual observation of length contraction. If you could photograph a rapidly moving object, it wouldn't appear simply contracted. Different parts of the object are seen by light emitted at different times, creating a rotation effect. A cube moving at relativistic speed appears rotated rather than simply compressed. This doesn't contradict length contraction measurements of the cube's length using synchronized clocks at both ends would show contraction, but visual appearance differs from actual length because observation involves light travel time effects. This subtlety delayed full understanding of how relativistic objects would actually look. No experiment has ever detected a violation of length contraction. Every measurement in particle physics assumes length contraction occurs as predicted, and every prediction matches observation. The standard model of particle physics, tested to extraordinary precision, incorporates length contraction fundamentally through the Lorentz transformation. If length contraction didn't occur, scattering cross-sections, decay rates, and particle production rates would all be wrong by factors of gamma or gamma squared. The theory works because length contracts. The invisibility of length contraction to direct observation doesn't make it less real than time dilation. Both are aspects of spacetime's four-dimensional structure, manifesting differently but equally fundamental. Time dilation can be measured by comparing a traveling clock to a stationary clock. Because clocks carry information through time, they accumulate differences that persist after motion stops. Length doesn't accumulate, it's measured at an instant. This difference in measurement method doesn't reflect a difference in reality. Both effects are required for the Lorentz transformations to preserve the space-time interval, and both are confirmed by countless indirect tests. The philosophical implications are profound. Length is not an intrinsic property of objects, but depends on the observer's state of motion. A meter stick doesn't have a true objective length. It has length 1 meter in its rest frame, 0.5 meters in a frame moving at 0, 866 c, and so on, all equally valid. This seems to contradict common sense, but common sense is wrong. Space and time are not absolute, fixed backgrounds, but flexible, observer-dependent quantities. Length contraction, along with time dilation and relativity of simultaneity, are consequences of space-time structure, as inevitable as the angles in a triangle summing to 180 degrees in flat space. The light cone that divides past from future. Hermann Minkowski introduced space-time diagrams in 1908 to visualize special relativity geometrically. In a Minkowski diagram, one axis represents space and the other represents time, typically with time running upward and space running horizontally. Each point in the diagram represents an event, a specific location, at a specific time. An object's motion through space-time traces a world line on the diagram. A stationary object has a vertical world line location doesn't change while time advances. A moving object has a tilted worldline with slope equal to 1 divided by velocity. No massive object can have worldline tilted more than 45 degrees because that would require velocity exceeding light speed. The 45-degree lines represent light rays. Since light travels at velocity c, and we typically scale diagrams so c equals 1 inch diagram units 1 second of time equals 1 light second of spacelight rays, follow 45-degree diagonal lines. These diagonals are called light cones because in 3 spatial dimensions plus time, they form 4-dimensional cone shapes. The future light cone contains all events that can be reached from a given event by traveling at or below light speed. The past light cone contains all events that could have sent signals to the given event at or below light speed. Events inside the future light cone are time-like separated from the origin event. The space-time interval between them is positive, defined as c squared times the time difference squared minus the spatial separation squared. For time-like separated events, more time elapses than would be needed for light to travel the spatial distance. Massive objects can travel between time-like separated events because their velocity can be less than c. The future light cone represents the region of spacetime that can be causally affected by the origin event signals, or particles emitted from the origin can reach these events. Events outside the light cone are space-like separated from the origin. The spacetime interval is negative spatial separation, exceeds ct, where t is the time difference. These events cannot be reached from the origin at or below light speed. No causal influence can connect space-like separated events because that would require faster than light signaling. Different observers disagree about the time ordering of space-like separated events. One observer might measure event A before event B, while another observer, moving differently, measures B before A. This relativity of simultaneity applies only to space-like separated events, never to time-like separated events. Events on the light cone itself are light-like separated or null separated. The space-time interval is exactly 0. The spatial separation equals exactly ct. Light rays and other massless particles follow null paths, always remaining on the light cone. The light cone defines the boundary between causally connected and causally disconnected regions of spacetime. Anything inside the light cone can influence or be influenced by the origin event. Anything outside cannot. The light cone structure is the geometrical manifestation of the universal speed limit. The light cone provides a natural way to understand why nothing can exceed light speed. Suppose an object could travel faster than light, moving from event A to event B outside A's light cone. We can find a reference frame where B occurs before A. Now suppose the object sends a signal back from B to A's past light cone, traveling again faster than light. This signal reaches A's past an event in the past light cone of A. The object has sent information to its own past, creating a causality violation. If you could send signals faster than light, you could send signals backward in time, potentially creating paradoxes where effects precede causes. Causality requires that the order of causally connected events that can influence each other, must be the same in all reference frames. Event A can cause event B only if A is in B's past light cone, ensuring A occurs before B in all frames. The Lorentz transformations preserve the light cone structure. If two events are time-like separated in one frame, they're time-like separated in all frames, and their time ordering is the same in all frames. If they're space-like separated in one frame, they're space-like separated in all frames, and different frames disagree about their time ordering. This structure enforces causality. The light cone structure is not just a mathematical convenience, but reflects spacetime's fundamental architecture. The existence of a maximum signal velocity, whether that velocity is c or some other value, inevitably creates light cone structures. If the maximum velocity were different, the cones would be tilted differently, but the same causal structure would exist. The specific value c equals 299,792,458 meters per second depends on our choice of units. The existence of a finite maximum velocity is what's fundamental, and that existence creates light cones that divide space-time into causally connected and causally disconnected regions. Closed time-like curves, paths through space-time that loop back to their starting event, violate causality if they exist. Such paths would allow an object to travel into its own past, creating paradoxes. The consistency of quantum mechanics with general relativity may require that closed time-like curves cannot form, or, if they do, quantum effects prevent macroscopic objects from following them. The light cone structure in special relativity guarantees closed time-like curves cannot exist in flat spacetime. They can potentially exist in exotic general relativistic spacetimes with unusual topologies, but whether they're physically possible remains uncertain. The light cone structure also explains why simultaneity is relative. For space-like separated events A and B, we can find reference frames where A occurs before B, simultaneously with B, or after B. This doesn't violate causality because A and B cannot influence each other. They're outside each other's light cones. Different observers can disagree about whether A or B happens first, but this disagreement has no physical consequences because no causal relationship connects them. For time-like separated events, all observers agree on time ordering, preserving causality even though different observers measure different time intervals between events. Minkowski's geometric interpretation revealed that special relativity is really a theory about space-time geometry, not about weird effects of motion. The Lorentz transformations are rotations in four-dimensional spacetime, analogous to spatial rotations in 3 dimensions. Just as rotating your perspective mixes x, y, and z coordinates without changing the distance between points, changing reference frames mixes space and time coordinates without changing the space-time interval between events. The light cone structure is preserved under Lorentz transformations, just as the surface of a sphere is preserved under spatial rotation. The causal structure enforced by light cones is one of physics' most fundamental principles. No known physical process, no interaction, no force, no influence can propagate faster than light. Electromagnetic forces propagate at c through photon exchange. The strong and weak nuclear forces propagate at c through gluon and W-Z boson exchange. Gravity propagates at c through graviton exchange. Gravitational waves, detected by LIGO in 2015, traveled at light speed to within 1 part in 10 to the 15th. If any interaction propagated faster than c, it would violate causality, allowing effects to precede causes and creating logical contradictions. The universe appears to be constructed to avoid such contradictions. The light cone structure has practical implications for communication and observation. The observable universe is limited by our past light cone. We can only observe events from which light has had time to reach us since the Big Bang 13.8 billion years ago. The particle horizon, the boundary of the observable universe, lies about 46.5 billion light-years away, farther than 13.8 billion light-years, because cosmic expansion stretched space while light traveled. We cannot communicate with regions beyond this horizon because they're outside our light cone. Similarly, we cannot influence events outside our future light cone. Those regions are causally disconnected from us. The light cone structure determines what we can observe, what we can influence, and what can influence us. The tachyons that might exist, but probably don't. In 1967, Gerald Feinberg, a physicist at Columbia University, published a paper titled Possibility of Faster-than-Light Particles in the journal Physical Review. Feinberg proposed a hypothetical class of particles called tachyons, from the Greek word tachys, meaning swift, that would always travel faster than light. Unlike ordinary particles that can never reach light speed because their energy would become infinite, tachyons would never be able to slow down to light speed because that would require infinite energy. Light speed would be an impassable barrier from above rather than below. Tachyons would inhabit a strange realm where they speed up when they lose energy and slow down when they gain energy. The mathematics of tachyons arises from extending special relativity to imaginary rest mass. The energy-momentum relation states that E squared equals the quantity mc squared plus the quantity pc squared. For ordinary particles with real mass m, this gives positive energy. For massless particles with m equals 0, energy equals momentum times c. But if we allow mass to be imaginary, m equals I times m, where I is the square root of -1, and m is a real positive number, then E squared equals -m squared c to the fourth plus p squared c squared. For sufficiently large momentum, energy can be real and positive. For tachyons with imaginary mass Im, the Lorentz factor gamma equals 1 divided by the square root of 1 minus phi squared over c squared becomes imaginary when v is less than c, because the expression under the square root is positive. But when v exceeds c, the expression 1 minus v squared over c squared becomes negative, making its square root imaginary, and dividing 1 by an imaginary number gives another imaginary number whose square is negative, making gamma real. This seemingly bizarre mathematics means tachyons have real energy and momentum only when traveling faster than light. Tachyon energy equals mc squared times the quantity v divided by the square root of v squared minus c squared. As velocity increases above c, energy decreases. As velocity approaches c from above, energy approaches infinity. The minimum tachyon energy occurs at infinite velocity, where energy equals max squared. This inverted behavior means tachyons speed up when they emit radiation and slow down when they absorb energy, opposite to ordinary particles. A tachyon losing energy accelerates toward infinite velocity. A tachyon gaining energy decelerates toward light speed, but can never reach it. Tachyons would violate causality if they could be controlled to send information. Suppose you send a tachyon signal from event A to event B outside A's light cone. Because B is space-like separated from A, there exists a reference frame where B occurs before A. An observer in that frame sees the tachyon traveling backward in time. Now, suppose someone at B sends a tachyon signal back to A's past light cone. This creates a causal loop. The signal arrives before it was sent, potentially creating a grandfather paradox where you could prevent your own signal from being sent. Several resolutions to this paradox have been proposed. One possibility: tachyons exist but cannot be controlled to send information. They might be produced randomly with random velocities and directions, making them useless for communication. Another possibility: tachyons always travel forward in time in all reference frames, violating Lorentz invariance. This would require a preferred reference frame, contradicting relativity, but avoiding causality violation. A third possibility: causality violations are possible, but self-consistency is enforced. The universe allows only self-consistent histories where causal loops don't create logical contradictions. No experimental evidence for tachyons has ever been found despite numerous searches. Early neutrino experiments in the 1970 seconds and 1980 seconds suggested neutrinos might travel faster than light, but these results were explained by experimental errors or reinterpreted as neutrino oscillations requiring small but non-zero mass. The OPERA experiment in 2011 announced neutrinos traveling from CERN to Gran Sasso Laboratory in Italy arrived 60 nanoseconds earlier than expected, suggesting faster than light velocity. But the result was traced to a faulty connection in the GPS system used for timing. Subsequent measurements showed neutrinos travel at light speed within experimental uncertainty. Particle accelerators have produced vast numbers of exotic particles, quarks, gluons, W and Z bosons, Higgs bosons, and more, but never tachyons. The Large Hadron Collider has observed millions of rare processes and decay modes, probing energies where tachyons might be produced if they existed. The complete absence of any faster-than-light particles strongly suggests they don't exist. If tachyons were common, some should have been detected accidentally in detectors designed for other purposes. The null result across decades of high-energy physics experiments constrains tachyon production cross-sections to undetectable levels, if they exist at all. Theoretical developments since 1967 have made tachyons seem less plausible. Quantum field theory with tachyons fields whose quanta are tachyons is unstable. The vacuum state has infinite energy, and the theory predicts spontaneous pair production of tachyons from vacuum, growing exponentially until the vacuum state changes. This tachyon condensation process doesn't produce observable faster-than-light particles, but instead shifts the vacuum to a different state. Modern understanding interprets imaginary mass fields as signals of instability, rather than descriptions of faster-than-light particles. String theory contains tachyons in certain formulations, specifically in bosonic string theory, and some versions of superstring theory. But these tachyons indicate that the theory is in an unstable state, not that faster-than-light particles exist. The tachyon field's instability drives the theory toward a stable vacuum where the tachyon disappears. This is analogous to a ball sitting on top of a hill, mathematically described by a potential with imaginary curvature. The ball rolls down the hill to a stable valley. String theory's tachyons are mathematical artifacts of expanding around an unstable point, not physical particles. The absence of tachyons fits with the light cone structure of spacetime. If tachyons existed and could be controlled, they would enable sending signals outside light cones, violating causality. The fact that no superluminal particles have been observed suggests that nature forbids them to preserve causality. This doesn't prove tachyons are impossible. Causality could be protected by making tachyons uncontrollable or by enforcing self-consistency. But Occam's razor suggests the simplest explanation. Tachyons don't exist because faster-than-light travel violates the fundamental structure of spacetime. Some physicists have speculated about tachyon-like objects that might exist without violating causality. One proposal involves particles that follow closed time-like curves in exotic spacetime geometries. Another involves quantum phenomena, where virtual particles briefly exceed light speed without carrying information. But these proposals remain highly speculative, with no experimental support. The mainstream physics consensus is that tachyons, if they existed, would require overthrowing or radically modifying special relativity, which has passed every experimental test for 119 years. Given this success and the absence of any evidence for superluminal particles, most physicists consider tachyons mathematical curiosities rather than physical realities. Feinberg's original paper was careful to note that tachyons might not exist despite being mathematically possible within relativity's framework. He wrote that the question of whether they exist is empirical, to be settled by experiment rather than theory. Nearly 60 years later, experiments have consistently answered no. While mathematical curiosity keeps tachyons in the physics literature, practical research has moved on. The absence of faster-than-light particles reinforces the light speed barrier's inviolability, not just for ordinary matter, but for all particles, fields, and interactions. Nature appears to respect this speed limit absolutely. The Cherenkov radiation, when particles beat local light speed. In 1934, Pavel Cherenkov, a Soviet physicist working at the Lebedev Physical Institute in Moscow, observed a strange blue glow in a bottle of water when it was exposed to radiation from a radioactive source. Initially, Cherenkov thought this might be some form of fluorescence, but careful measurements showed the light had peculiar properties. It was emitted in a specific direction at a characteristic angle, and its intensity didn't decrease significantly over time as fluorescence would. Further investigation revealed that fast-moving charged particles traveling through the water were producing the light, a phenomenon now called Cherenkov radiation. Cherenkov radiation occurs when a charged particle travels through a medium faster than light travels in that same medium. Light speed in vacuum is c, but in materials with refractive index n greater than 1, light travels at c divided by n. Water has refractive index about 1.33, so light travels at 225,000 kilometers per second in water 75% of its vacuum speed. A charged particle, like an electron, can easily reach 0.9c in vacuum or 270,000 kilometers per second. When such a particle enters water, it's moving at 270,000 kilometers per second, while light in water travels at only 225,000 kilometers per second. The particle exceeds the local light speed. When a particle exceeds local light speed, it creates a shockwave of electromagnetic radiation, analogous to a sonic boom when an aircraft exceeds the speed of sound. As the particle moves, it continuously disturbs the electromagnetic field in the medium. These disturbances normally propagate outward at the local light speed and interfere destructively, producing no net radiation. But when the particle moves faster than the disturbances can propagate, the disturbances pile up constructively at a specific angle, creating a shockwave Cherenkov radiation emitted at a characteristic angle to the particle's direction of motion. The Cherenkov angle, the angle between the emitted light and the particle's direction, depends on the particle's velocity and the medium's refractive index. The cosine of the Cherenkov angle equals 1 divided by n times beta, where beta equals v over c. For a particle traveling at 0.9 c in water with n equals 1.33, beta equals 0.9, so cosine of the angle equals 1 divided by 1.197, which equals 0.835. This gives an angle of about 33 degrees. The light forms a cone around the particle's path, creating the characteristic blue glow seen in nuclear reactor cooling pools. Cherenkov radiation appears blue because the intensity depends on wavelength. The radiated power per unit wavelength is proportional to 1 over wavelength squared. Shorter wavelengths radiate more intensely than longer wavelengths. Blue and violet light, with wavelengths around 400 to 500 nanometers, radiate much more strongly than red light at 700 nanometers. This wavelength dependence makes Cherenkov light distinctly blue. Similar to why the sky is blue, both phenomena involve scattering or radiation mechanisms that favor shorter wavelengths. Nuclear reactor pools glow blue from Cherenkov radiation produced by energetic electrons emitted during radioactive decay. Fission products in the reactor's fuel emit beta particles, electrons and positrons, with energies up to several million electron volts. These particles enter the surrounding water at relativistic velocities around 0.9 c to 0.99 c, exceeding water's light speed of 0.75 c. The resulting Cherenkov radiation creates an eerie blue glow around the reactor core, visible through the clear water to observers standing by the pool's edge. The glow is beautiful but dangerous, indicating intense radiation that would be lethal without the water's shielding. Igor Tamm and Ilya Frank developed the theory explaining Cherenkov radiation in 1937, shortly after Cherenkov's discovery. They showed that classical electromagnetism predicts this radiation when particles exceed the local light speed, and they derived formulas for the emission angle and intensity. For this work, Cherenkov, Frank, and Tamm shared the 1958 Nobel Prize in Physics. The theoretical explanation was crucial because it confirmed that the phenomenon was a real electromagnetic effect, not some unknown type of fluorescence or luminescence. Cherenkov detectors exploit this radiation to detect and measure high-energy particles. The Super Kamiokande detector in Japan consists of a cylindrical tank 40 meters diameter and 40 meters tall, filled with 50,000 tons of ultra-pure water and lined with 11,000 photomultiplier tubes. When a neutrino interacts with a water molecule, it can produce a charged lepton electron or muon traveling faster than light speed in water. This charged lepton emits Cherenkov radiation detected by the photomultiplier tubes. The arrival times and positions of detected photons allow reconstruction of the particle's direction, energy, and type. The IceCube Neutrino Observatory at the South Pole uses Antarctic ice as a Cherenkov detector. The facility deployed 5,160 optical sensors on strings buried 1.5 to 2.5 kilometers deep in the ice, instrumenting a cubic kilometer volume. When a high-energy neutrino interacts in or near the detector, it produces a muon that travels through the ice faster than light speed in ice which has refractive index about 1.31, giving local light speed 230,000 kilometers per second. The muon's Cherenkov light is detected by the optical sensors, revealing the neutrino's direction and energy. Cherenkov radiation from cosmic rays creates brief flashes of light in Earth's atmosphere that can be detected from the ground. When ultra-high energy cosmic rays, protons or nuclei, with energies exceeding 10 to the 15th electron volts, strike the upper atmosphere, they create extensive air showers consisting of thousands or millions of secondary particles. Many of these particles travel through air faster than light speed in air, which is 299,700 kilometers per second due to air's refractive index of 1.0003. The resulting Cherenkov light flashes last only nanoseconds but can be detected by specialized telescopes. The Very Energetic Radiation Imaging Telescope Array System, or VERITAS, in Arizona uses 4 12-meter optical telescopes to detect atmospheric Cherenkov light from gamma-ray air showers. When a gamma ray with energy above 100 giga-electron volts strikes the atmosphere, it creates an electromagnetic cascade of electrons and positrons. These particles exceed the air's light speed, producing Cherenkov light that reaches the ground in a pool roughly 100 meters diameter. Veritas's cameras capture images of this light, reconstructing the incoming gamma ray's energy and direction. Observations reveal gamma ray sources, including supernova remnants, pulsars, and active galactic nuclei. Cherenkov radiation is often misunderstood as violating relativity by allowing particles to exceed light speed. But there's no violation. The particles never exceed c, the speed of light in vacuum. They only exceed c over n, the speed light happens to travel in that particular medium. Special relativity's requirement that nothing exceeds c applies to the vacuum light speed, not the medium light speed. The medium slows light through interactions with atoms, but particles in the medium experience only electromagnetic forces and can exceed the slowed light speed without violating relativity. The observation of Cherenkov radiation provides an elegant confirmation that light speed depends on the medium. If light always traveled at c regardless of medium, Cherenkov radiation wouldn't exist. Particles could never exceed light speed. The fact that Cherenkov radiation occurs, with angles and intensities matching theoretical predictions based on medium refractive indices, confirms that light slows in materials while particles don't slow as much. This validates both special relativity and electromagnetic theory's description of light propagation in matter. The quantum entanglement that doesn't send information. Quantum entanglement is a phenomenon where two particles share a quantum state such that measuring one particle instantly affects the other, regardless of separation distance. When two particles are entangled, created together in a specific way, or brought into interaction, and then separated measuring a property of one particle immediately determines the corresponding property of the other particle. If you measure one particle's spin and find it pointing up, the other particle's spin is instantly down. This correlation exists even if the particles are separated by kilometers or light years, suggesting some kind of faster than light influence between them. Albert Einstein, Boris Podolsky, and Nathan Rosen described this in their famous 1935 paper, Can Quantum Mechanical Description of Physical Reality Be Considered Complete? Einstein called it spooky action at a distance and argued it proved quantum mechanics was incomplete. They reasoned that if measuring particle A instantly affects particle B light years away, either information travels faster than light violating relativity, or the particles possessed hidden properties from the beginning that determined their measurement outcomes. Einstein favored hidden variables over faster than light influences, believing quantum mechanics missed some underlying reality. John Stuart Bell formulated a way to test this in 1964. Bell's theorem shows that any theory with local hidden variables, properties particles possess before measurement, with no faster than light influences, must satisfy certain mathematical inequalities relating measurement probabilities at different angles. Quantum mechanics predicts violations of these Bell inequalities. The predictions differ. Hidden variable theories satisfy Bell's inequalities, while quantum mechanics violates them. This makes the question experimentally decidable. Measuring correlations at specific angles reveals which theory is correct. Alain Aspect performed definitive tests of Bell's inequalities starting in 1982 at the Institut d'Optique in Paris. Aspect's experiments used entangled photon pairs created by calcium atoms. The photons traveled to detectors 12 meters apart, where their polarizations were measured at various angles. The experiments included crucial improvements: fast switching of measurement angles while photons were in flight, ensuring the choice of angle at one detector couldn't influence the other detector through any signal traveling at light speed. Results clearly violated Bell's inequalities by many standard deviations, confirming quantum mechanical prediction. The violation of Bell's inequalities means that either locality fails, allowing faster than light influences, or realism fails, particles don't have definite properties before measurement. Most physicists accept that realism fails. Quantum particles don't possess definite spin values before measurement. The measurement itself creates the outcome, and entanglement ensures the outcomes are correlated. This interpretation preserves locality no faster than light influences, at the cost of abandoning the intuition that particles have properties independent of observation. Crucially, entanglement cannot send information faster than light. When you measure one particle's spin, you indeed instantly know the other particle's spin. But the person at the other particle doesn't know you've made a measurement. They see random results 50% up, 50% down with no pattern. Only when you compare measurements later, using conventional slower-than-light communication, do the correlations become apparent. The entanglement correlates outcomes but doesn't allow signaling. You can't encode information into your measurement choice in a way that affects the statistics the other observer sees. This inability to signal through entanglement follows from quantum mechanics linearity and the no communication theorem, proven by Philippe Eberhard in 1978. The theorem shows that in any quantum theory, local measurements cannot affect the statistics of distant measurements. You can choose what to measure and affect your own outcome probabilities, but you can't affect anyone else's statistics regardless of entanglement. The correlations appear only in joint measurements after comparing results through classical communication. This preserves causality and prevents entanglement from enabling faster than light information transfer. Quantum teleportation provides another example where quantum effects seem to violate locality but actually don't. In quantum teleportation, an unknown quantum state is transferred from one particle to another distant particle using entanglement and classical communication. The process seems to transfer information instantly, but it requires sending classical information about measurement results through normal channels limited to light speed. The distant particle remains in a random state until the classical information arrives and is used to perform a unitary operation. Teleportation is impossible without the classical communication step. Experiments have demonstrated entanglement over increasing distances, testing whether correlations weaken with separation. In 2017, Chinese researchers reported entanglement between photons separated by 1,200 kilometers using the Messius satellite. One photon from an entangled pair was sent to a ground station in Delinga, while the other went to a station in Lijiang. Measurements violate Bell inequalities with the same magnitude as short-distance experiments, confirming entanglement persists over satellite distances. The correlations show no measurable degradation, with distance a property called monogamy of entanglement. The speed of entanglement correlations has been tested directly. If the apparent faster-than-light correlation occurred through some signal traveling at finite but very high speed, there should be a delay proportional to distance. Experiments place lower bounds on this hypothetical signal speed at more than 10,000 times c, effectively instantaneous within experimental precision. This is consistent with quantum mechanics, which predicts no delay regardless of distance. The instant correlation doesn't violate relativity because no information transfers, the outcomes are random until compared. Entanglement is now routinely used in quantum communication and quantum computing. Quantum key distribution protocols use entangled photons to establish secure encryption keys. Any eavesdropping attempt disturbs the entanglement, revealing the security breach. Quantum computers use entanglement between qubits to achieve computational speedups over classical computers. While these applications exploit quantum correlations, none allow faster-than-light communication. They use entanglement for computational or cryptographic purposes, always constrained by the no-communication theorem that prevents signaling through quantum correlations. The philosophical implications of entanglement are profound. Reality at the quantum level is non-local, in the sense that measurement outcomes are correlated instantaneously across space. But this non-locality doesn't violate causality, because the correlations can't be controlled to send information. Einstein's concern about spooky action at a distance was partially justified. Quantum mechanics does have non-local aspects. But his conclusion was wrong. The non-locality doesn't conflict with relativity because it can't be used for signaling. Quantum mechanics and special relativity are compatible, both correct within their domains, with quantum field theory unifying them completely. The key lesson: correlation is not causation, and instant correlation doesn't imply faster than light causation. When you measure one particle and instantly know the other's state, you haven't caused the distant state, it was determined by the entanglement created when the particles interacted. The instant knowledge reflects the pre-existing correlation, not a causal influence propagating faster than light. This distinction preserves causality and the light speed limit, while allowing quantum mechanics' strange non-local correlations. The universe can have instant correlations without causal influences, exceeding light speed, a subtlety that resolves the apparent contradiction between quantum mechanics and relativity. The space-time expansion that isn't bound by light speed. In 1929, Edwin Hubble discovered that distant galaxies are receding from us, with recession velocity proportional to distance. This relationship, now called Hubble's law, states that velocity equals the Hubble constant times distance v equals h0 times d. The current best measurement of the Hubble constant from the Planck satellite's observations of the cosmic microwave background gives 67.4 kilometers per second per megaparsec. 1 megaparsec equals 3.26 million light-years, so for every 3.26 million light-years of distance, recession velocity increases by 67.4 kilometers per second. At sufficient distance, this relationship produces recession velocities exceeding light speed. Calculate the distance where recession velocity equals light speed 299,792 kilometers per second divided by 60, 7.4 kilometers per second per megaparsec equals 4,450 megaparsecs, or about 14.5 billion light-years. Galaxies farther than this distance recede faster than light. The observable universe extends to about 46.5 billion light-years, the comoving distance to the cosmic horizon. Galaxies at this distance recede at approximately 2 times light speed. This doesn't violate relativity because galaxies aren't moving through space faster than light. Space itself is expanding, carrying galaxies with it. The distinction between motion through space and expansion of space is fundamental. Special relativity's speed limit applies to motion through space objects moving relative to their local spacetime. But general relativity, Einstein's theory of gravity published in 1915, describes how spacetime itself can curve and evolve. The expansion of the universe is spacetime itself stretching, increasing distances between galaxies, while the galaxies remain essentially at rest in their local reference frames. No galaxy moves through its local spacetime faster than light, preserving special relativity locally, even as cosmic expansion makes distant galaxies recede superluminally. An analogy: imagine dots painted on a rubber sheet. If you pull the sheet's edges, the dots move apart. Dots far apart separate faster than nearby dots. Eventually, dots become so far apart that the sheet's expansion rate exceeds any speed limit for objects moving across the sheet's surface. But individual dots don't violate the speed limit. They remain at rest on the sheet, while the sheet itself stretches. Cosmic expansion works similarly. Galaxies remain at rest in their local spacetime, while spacetime expands, increasing distances at rates that can exceed light speed for sufficiently separated galaxies. The cosmic expansion is described by the Friedmann-Lemaitre-Robertson-Walker metric, a solution to Einstein's field equations discovered independently by Alexander Friedmann in 1922 and Georges Lemaitre in 1927. This metric describes a homogeneous, isotropic expanding universe where space has a scale factor that increases with time. The scale factor's growth rate determines the Hubble constant. As the scale factor increases, the proper distance between any two galaxies grows proportionally, creating the distance-velocity relationship Hubble observed. The metric contains no coordinate velocities exceeding light speed. All motion is subluminal in local reference frame. Galaxies beyond the Hubble radius, the distance where recession velocity equals light speed, are observable because they were closer in the past when the universe was smaller. Light emitted from these galaxies traveled toward us, but expansion carried the galaxies away faster than light. Initially, the light made no progress toward us, even moving away. But expansion has been slowing, or more recently, accelerating at a different rate, such that light eventually entered regions where recession velocity was less than light speed. Once in such regions, light made progress toward us, eventually arriving after billions of years of travel. The particle horizon at 46.5 billion light-years represents the maximum distance from which light could have reached us since the Big Bang 13.8 billion years ago. Light from farther cannot have arrived yet, making those regions unobservable. The particle horizon distance exceeds 13.8 light-years because space expanded while light traveled. A photon emitted 13.8 billion years ago, at the beginning of the universe, traveled 13.8 billion light-years through space. But expansion stretched the distance between its emission point and us to 46.5 billion light-years. The co-moving distance, accounting for expansion, differs from the light travel distance. Dark energy, discovered through supernova observations in 1998, accelerates cosmic expansion. Two teams, the Supernova Cosmology Project, led by Saul Perlmutter, and the High Z Supernova Search Team, led by Brian Schmidt and Adam Riess, independently found that distant supernovae appeared dimmer than expected, indicating they were farther away than predicted by a decelerating universe. This implied acceleration, driven by an unknown energy with negative pressure that fills space and pushes space apart. Dark energy comprises about 68% of the universe's total energy density. Accelerating expansion has profound implications. In a decelerating universe, the Hubble radius grows faster than the universe expands, eventually encompassing all galaxies and allowing light from any galaxy to eventually reach any other. But in an accelerating universe, dominated by dark energy, the Hubble radius approaches a constant value. Galaxies beyond this radius recede faster than light permanently. Light they emit now will never reach us. We're causally disconnected from them. These galaxies fade from view as expansion carries them beyond our cosmic horizon, leaving only their ancient light that was already en route. The expansion rate varies with time. In the early universe dominated by radiation, expansion decelerated rapidly. During the matter-dominated era from about 50,000 years to 9 billion years after the Big Bang, expansion decelerated more slowly. Since about 5 billion years ago, dark energy has dominated, and expansion has accelerated. The Hubble constant, actually not constant, but changing with time, was much larger in the early universe. At redshift Z equals 1000 shortly after recombination, when the cosmic microwave background formed, the Hubble constant was roughly 23,000 times larger than today, meaning expansion was much faster. Galaxies have peculiar velocities, random motions relative to the cosmic expansion, typically a few hundred kilometers per second. The Andromeda Galaxy approaches the Milky Way at 110 kilometers per second, despite cosmic expansion trying to push us apart. This local motion dominates over expansion at small scales, where gravitational attraction overcomes expansion. The local group of galaxies is gravitationally bound, not expanding. Only on scales above about 100 million light-years does expansion dominate over local gravitational effects. Within galaxy clusters, galaxies orbit each other and the cluster's center, ignoring expansion. The concept of velocity becomes ambiguous in an expanding universe. For nearby galaxies where expansion is slow, we can meaningfully define velocity as distance change per time. But for distant galaxies, different definitions give different answers. Proper distance, the distance measured by a chain of observers at a single time, changes due to expansion. Comoving distance, distance in coordinates that expand with the universe, remains constant for galaxies at rest in the cosmic expansion. Light travel distance, how far light has traveled, differs from both. Each definition serves different purposes, and none is uniquely correct. The cosmic expansion doesn't violate special relativity, because special relativity applies only to motion through spacetime, not to spacetime evolution itself. General relativity encompasses both motion through spacetime and spacetime dynamics. In general relativity, the constraint that massive objects cannot exceed light speed means they cannot move faster than light relative to their local reference frame. But spacetime itself can expand or contract. At any rate, there's no speed limit for spacetime geometry evolution. Local physics obeys special relativity, including the light speed limit, while global spacetime structure follows general relativity, allowing superluminal recession. Future observations will probe cosmic expansion with increasing precision. The Large Synoptic Survey Telescope, renamed the Vera-C, Rubin Observatory, will survey billions of galaxies and thousands of supernovae, mapping expansion history from the present back to when the universe was 1/10 its current age. The James Webb Space Telescope, launched in 2021, observes the most distant galaxies yet detected at redshifts exceeding 10, probing the universe when it was only 500 million years old. These observations constrain dark energy properties and test whether acceleration is caused by a cosmological constant or something more exotic. The expansion rate's cosmic history is encoded in the distance redshift relationship. Redshift Z measures how much light has been stretched by expansion wavelength multiplied by 1 plus Z. Nearby galaxies at 100 million light-years have tiny redshifts around 0.007. The cosmic microwave background at 46.5 billion light-years has redshift 1000, 100 light stretched by factor of 1000, 100 since emission. The highest redshift galaxies observed approach redshift 14, with light stretched by factor of 15. Mapping distance versus redshift reveals how expansion rate changed with time, testing cosmological models and constraining dark energy. The Alcubierre drive that might work on paper. In 1994, Miguel Alcubierre, a Mexican theoretical physicist then at Cardiff University, published a paper proposing a speculative method for faster-than-light travel that doesn't violate relativity. The Alcubierre drive works by contracting space-time ahead of a spacecraft and expanding space-time behind it, creating a bubble of flat space-time around the ship that moves faster than light through the warped space-time outside the bubble. Inside the bubble, the ship remains at rest relative to its local space-time and experiences no time dilation, acceleration forces, or relativistic effects. The ship surfs a wave of space-time distortion, achieving effective, faster-than-light travel without moving through space-time faster than light. Alcubierre's metric is a solution to Einstein's field equations, the mathematical equations governing how matter and energy curve spacetime. The metric describes a spacetime geometry where the spatial distance between 2 points changes with time due to expansion behind and contraction ahead. The ship sits in a region of flat spacetime, experiencing no forces, while spacetime flows past it at velocities that can exceed c. From the ship's perspective, it remains stationary. From an external observer's perspective, the ship moves faster than light. Both perspectives are valid. The apparent contradiction resolves through the distinction between motion through spacetime and spacetime evolution. The warp bubble requires exotic matter with negative energy density to create the spacetime distortion. In general relativity, positive energy density curves spacetime one way, producing gravitational attraction. Negative energy density curves spacetime the opposite way, producing gravitational repulsion. The Alcubierre metric requires a thin shell of negative energy surrounding the bubble. With energy density roughly -1 Jupiter mass per cubic meter, enormous negative energy, concentrated in a thin region. No known form of matter or energy has negative energy density on macroscopic scales, making the drive speculative at best. Quantum field theory allows small negative energy densities through the Casimir effect, discovered by Hendrik Casimir in 1948 and measured by Stephen Lamoureux in 1997. The Casimir effect arises from vacuum fluctuations, virtual particles constantly appearing and disappearing in empty space. Between two conducting plates placed nanometers apart, fewer vacuum fluctuation modes fit than in open space, creating lower energy density between the plates than outside. This energy density difference produces an attractive force between plates, measured at about 1 micronewton for square centimeter plates, separated by 1 micrometer. The Casimir energy density between plates is negative relative to the vacuum outside, but only by tiny amounts, around 10 to the -6 joules per cubic meter at 1 micrometer separation. Alcubierre's drive requires energy densities around 10 to the 35th joules per cubic meter negative energy, 41 orders of magnitude larger than Casimir achieves. The quantum inequality theorem, derived by Larry Ford and Thomas Roman in the 1990 seconds, constrains how much negative energy can accumulate and for how long. The bounds make macroscopic warp bubbles impossible according to known physics, though loopholes might exist in quantum gravity regimes where the theorem's assumptions break down. Even if negative energy could be obtained, the required amount is staggering. Alcubierre's original calculation suggested energy equivalent to the mass of Jupiter, about 2 times 10 to the 27th kilograms times c squared, or roughly 2 times 10 to the 44th joules. Subsequent refinements by Chris van den Broek in 1999 reduced requirements by choosing different bubble shapes, getting the energy down to solar mass scales, or below, by making the bubble's interior arbitrarily small. But even reducing requirements to one solar mass 2 times 10 to the 30th kilograms represents 1.8 times 10 to the 47th joules, or roughly 400 trillion times total energy humanity has ever produced. Creating and controlling the warp bubble poses additional challenges. The bubble must form around the ship, requiring the ship to somehow manipulate space-time geometry in its vicinity. But causality prevents the ship from sending signals outside the bubble. The bubble's event horizon prevents light from the ship reaching the bubble's leading edge, where space-time contracts. The ship cannot control or steer the bubble once inside. Some proposals suggest pre-existing infrastructure stationary emitters that create and guide the bubble, but this requires infrastructure spanning interstellar distances, negating much of the faster-than-light travel benefit. Alcubierre drive travel might accumulate deadly blue-shifted radiation on the bubble's leading edge. As the bubble moves through space, it encounters ambient photons and particles from the cosmic microwave background, starlight, and interstellar gas. From the bubble's perspective, these particles are blue-shifted to high energies gamma rays and beyond due to the extreme relative velocity. The particles accumulate on the bubble's surface. When the bubble stops or dissipates, the accumulated radiation blasts forward, potentially destroying anything in its path, including the destination. This effect, analysed by Brendan McMonagle and colleagues in 2012, makes the drive impractical and dangerous. Causality violations remain a concern even if the drive is possible. Because the Alcubierre metric creates closed time-like curves paths through space-time that loop back to their starting event, it potentially allows time travel. If two warp bubbles accelerate in opposite directions, reach distant locations, then return, they can arrive back at their starting point before they left according to some reference frames. This creates the grandfather paradox. You could return and prevent your own departure. Such causal paradoxes suggest the drive might be impossible even if negative energy could be obtained, with unknown physics preventing closed time-like curves. Alcubierre himself has noted that his metric is a mathematical curiosity, demonstrating that general relativity allows superluminal effective velocities, not a practical propulsion proposal. He wrote in 2000 that the construction of such a device is probably impossible within the framework of known physics. The drive serves as a thought experiment showing what space-time geometry's general relativity permits, highlighting the theory's flexibility and raising questions about energy conditions that forbid certain geometries. Most physicists view the Alcubierre drive as interesting mathematics that reveals how general relativity differs from special relativity while likely being physically unrealizable. Variants of the Alcubierre drive have been proposed, attempting to reduce energy requirements or avoid causality violations. The Natario drive, proposed by Jose Natario in 2002, uses a different space-time geometry, achieving similar results with potentially lower energy. The Krasnikov tube, proposed by Sergei Krasnikov in 1995, creates a permanent tunnel through space-time connecting two regions, allowing faster-than-light travel through the tunnel. All these proposals require exotic matter and face similar challenges: enormous energy requirements, causality issues, and questionable physical realizability. They demonstrate that general relativity is rich enough to accommodate faster-than-light geometries while likely forbidding their actual construction. NASA's Advanced Propulsion Physics Laboratory, or EAGLE Works, led by Harold White, conducted theoretical and experimental investigations of warp drive concepts from 2012 to 2018. White proposed modifications to Alcubierre's geometry that might reduce energy requirements. EagleWorks attempted to detect space-time distortions using laser interferometry with claimed success, but the results were not independently replicated, and the project was later defunded. Most physicists consider the EagleWorks experiments inconclusive at best, unlikely to have detected actual space-time warping, given the minuscule energies involved far below what quantum field theory allows for macroscopic space-time distortion. The Alcubierre drive remains popular in science fiction despite its implausibility, providing a scientifically grounded, faster-than-light mechanism that doesn't obviously violate relativity. Star Trek's warp drive operates on similar principles, though without detailed physics. The appeal is understandable. The drive offers faster-than-light travel while respecting relativity's local constraints, avoiding time dilation and infinite energy requirements that plague conventional, faster-than-light proposals. But the requirement for exotic matter and the causality violations make it fantasy, not future technology, an interesting mathematical construct showing general relativity's boundaries rather than a roadmap to interstellar travel. The wormholes that connect distant points. In 1916, shortly after Einstein published General Relativity, Karl Schwarzschild found the first exact solution to Einstein's field equations describing spacetime around a spherically symmetric mass. This Schwarzschild solution included a curious feature. The geometry had two asymptotically flat regions connected by a throat. In modern language, the solution described a wormhole, a tunnel, through spacetime connecting two distant locations. But Schwarzschild's wormhole was non-traversable. The throat pinches off faster than light can cross it, preventing anything from going through. Objects entering from one side reach infinite density at the throat and emerge in a disconnected region unreachable from the original spacetime. Albert Einstein and Nathan Rosen revisited this in 1935, proposing what they called an Einstein-Rosen bridge as a model for particles. They suggested particles might be wormholes connecting regions of space-time, with the throat representing the particle's quantum nature. This proposal didn't lead anywhere productive, but it established wormholes as legitimate solutions to Einstein's equation. The term wormhole was coined much later by John Wheeler in 1957, describing these space-time tunnels as shortcuts through space-time analogous to a worm boring through an apple rather than crawling across its surface. Most naturally occurring wormhole solutions to Einstein's equations, without added constraints, are non-traversable. They either pinch off before anything can cross, or they contain singularities that destroy anything attempting passage, or they're one-way throats where objects can enter but not exit. The Schwarzschild wormhole connects a black hole in one region to a white hole in another region. A white hole being a time-reversed black hole that expels matter but cannot be entered. No observer can traverse this wormhole because the throat requires faster than light travel to cross before it pinches off. In 1988, Kip Thorne and colleagues published a paper exploring traversable wormholes in Physical Review Letters. They showed that wormholes could theoretically be kept open for traversal if exotic matter with negative energy density lined the throat, preventing gravitational collapse. The required negative energy density is comparable to what's needed for Alcubierre drives enormous amounts concentrated in specific geometries. The Thorne wormhole became a template for science fiction wormholes, notably influencing Carl Sagan's novel Contact, published in 1985, for which Thorne provided scientific consultation. A traversable wormhole connects two mouths openings through a throat that can be crossed in finite proper time by an observer traveling slower than light through the throat's interior. From outside, the mouths appear as spherical surfaces, perhaps mistakable for black holes, but lacking event horizons. An observer approaching a mouth sees through to the region near the other mouth, perhaps light years distant. Entering the mouth and traveling through the throat, the observer emerges from the other mouth, having crossed vast distances in short proper time achieving effective faster-than-light travel without violating special relativity locally. Wormholes enable time travel if the mouths can be moved relative to each other. Suppose you have a wormhole with mouths initially at rest near each other. Move one mouth away at relativistic velocity and return it. Due to time dilation, less time passes on the moving mouth than the stationary mouth. They age differently. Now the wormhole connects two locations at different times. Going through from the stationary mouth leads to the past, as measured by clocks near the moving mouth. This creates a time machine, allowing travel to the past and raising causality paradoxes. The grandfather paradox illustrates the problem. Enter the wormhole, travel to the past, prevent your grandfather from meeting your grandmother, thereby preventing your own birth and making it impossible for you to have entered the wormhole to begin with. This logical contradiction suggests time travel might be impossible or requires self-consistency. Only histories without logical contradictions can occur. Stephen Hawking proposed the chronology protection conjecture in 1992, suggesting unknown physics prevents time machines from forming. Possible mechanisms include quantum vacuum fluctuations becoming infinite as a time machine forms, destroying it before it can operate. Even without time travel, traversable wormholes face severe problems. The exotic matter requirement is daunting negative energy density far beyond what quantum field theory allows on macroscopic scales. The quantum inequality theorem constrains negative energy accumulation, likely making wormhole-sized regions of negative energy impossible. Additionally, wormholes are generically unstable. Small perturbations cause runaway growth, collapsing the wormhole or transforming it into a black hole. Matt Visser showed in 1989 that stabilizing a wormhole requires fine-tuned exotic matter distributions that adjust dynamically to perturbations, probably unachievable. No observational evidence for natural wormholes exists. If wormholes formed in the early universe or during black hole formation, they might persist. Primordial wormholes could exist scattered throughout space, but searches using gravitational lensing wormholes should produce distinctive lensing patterns different from black holes have found nothing. If a wormhole mouth existed in the solar system, we'd notice gravitational anomalies in planetary orbits. The absence of any such anomalies constrains wormhole abundance to essentially zero in our cosmic neighborhood. Quantum wormholes might exist at the Planck scale, 10 to the minus 35th meters, where quantum gravity effects dominate. At these scales, space-time itself might foam with quantum fluctuations, including tiny wormholes constantly forming and disappearing, lasting only 10 to the minus 43rd seconds. These quantum wormholes contribute to vacuum energy that can't be traversed. They're far too small and transient. Macroscopic wormholes would require scaling up quantum wormholes by 40 orders of magnitude, likely impossible without physics beyond general relativity and quantum field theory. Recent developments in quantum mechanics suggest entanglement and wormholes might be related through the ER equals EPR conjecture proposed by Juan Maldacena and Leonard Susskind in 2013. ER refers to Einstein-Rosen-Bridges wormholes. EPR refers to Einstein-Podolsky-Rosen entanglement. The conjecture suggests entangled particles are connected by non-traversable quantum wormholes. Entanglement is the manifestation of tiny wormholes linking particles. This remains speculative, but hints that wormholes and quantum mechanics might unify in quantum gravity without enabling classical traversal or faster-than-light travel. Wormholes appear frequently in science fiction because they provide a plausible-sounding faster-than-light mechanism rooted in real physics. Unlike warp drives that require active propulsion, wormholes are passive shortcuts, fixed infrastructure, enabling rapid transit. Science fiction often handwaves the exotic matter requirement or assumes advanced civilizations can manipulate space-time geometry. Interstellar The 2014 film, for which Kip Thorne was scientific consultant, depicted a wormhole placed near Saturn by unknown beings, providing realistic visualization of what approaching and traversing a wormhole would look like, complete with gravitational lensing effects. From a practical standpoint, wormholes almost certainly cannot exist as traversable structures based on known physics. The exotic matter requirement conflicts with quantum field theory. The instabilities make long-term existence impossible. The causality violations create logical contradictions. While general relativity permits wormhole geometries mathematically, quantum gravity, the unknown theory unifying quantum mechanics and general relativity, likely forbids them or renders them non-traversable. Wormholes remain fascinating theoretical constructs revealing spacetime's geometric richness, while probably being physically impossible, joining the Alcubierre drive as mathematically consistent but practically unrealizable, faster than light mechanisms. The energy requirements that make it impossible, the kinetic energy required to accelerate an object to relativistic velocities, grows exponentially near light speed, making faster than light travel energy prohibitive even if it were theoretically possible. For a 1 kilogram mass, the kinetic energy equals the quantity gamma minus 1 times rest energy, where rest energy equals 1 kilogram times c squared, or 9 times 10 to the 16th joules. At 0.9 c, where gamma equals 2.29, kinetic energy equals 1.29 times 9 times 10 to the 16th joules, or about 1.2 times 10 to the 17th joules, roughly 28 megatons of TNT equivalent. Accelerating just 1 kilogram to 0.9 c requires energy equal to history's largest nuclear weapon, the Tsar Bomba, at 50 megatons. At 0.99 c, where gamma equals 7.09, the 1 kilogram kinetic energy becomes 6.09 times 9 times 10 to the 16th joules, or 5.5 times 10 to the 17th joules, about 130 megatons TNT equivalent. At 0.999 c, where gamma equals 22.4, kinetic energy reaches 21.4 times 9 times 10 to the 16th joules, or 1.9 times 10 to the 18th joules, about 460 megatons. Each factor of 1 zero closer to light speed roughly multiplies required energy by 3. At 0.999 c, kinetic energy exceeds 6 times 10 to the 18th joules. The energy requirements become astronomical, exceeding total energy available from any plausible power source. Total world energy consumption is approximately 5.8 times 10 to the 20th joules per year as of 2024. Accelerating 1 kilogram to 0.999 c requires 1.9 times 10 to the 18th joules, about 0.3% of annual world energy. Accelerating a 1,000 kilogram spacecraft, tiny by space travel standards, to 0.999 c requires 1.9 times 10 to the 21st joules, more than 3 times world annual energy consumption. A realistic crewed spacecraft, massing perhaps 100,000 kilograms, would require 1.9 times 10 to the 23rd joules, about 330 times world annual energy. Getting to 0.999 c multiplies these by another factor of 3. Antimatter provides the highest energy density theoretically achievable. 100% mass energy conversion through matter-antimatter annihilation. Annihilating 1 kilogram of matter with 1 kilogram of antimatter yields 2 kilograms times c squared, or 1.8 times 10 to the 17th joules, enough to accelerate about 1.5 kilograms to 0.9 c, or 0.3 kilograms to 0.99 c, accounting for the need to carry antimatter fuel. A spacecraft must carry fuel, and the fuel's mass counts toward total mass that must be accelerated. dramatically worsening the energy budget through the rocket equation. The relativistic rocket equation describes how velocity depends on mass ratio, the initial mass, including fuel, divided by final mass after burning fuel. For exhaust velocity equal to c, the maximum possible for photon rockets or antimatter drives, the equation gives final velocity equals c times the quantity initial mass divided by final mass minus final mass divided by initial mass, all divided by initial mass divided by final mass plus final mass divided by initial mass. For mass ratio 2 burning half the spacecraft's mass as fuel final velocity reaches 0. 6c. For mass ratio 10, final velocity reaches 0, 98c. Reaching 0, 999c requires mass ratio around 50. The spacecraft must be 98% fuel by mass. Even with antimatter propulsion at 100% efficiency, a spacecraft carrying 98% of its mass as antimatter fuel plus matter for annihilation can only reach 0, 999c. The remaining 2% include structure, payload, crew, life support, and power systems extremely mass limited. For a 1,000 kilogram payload, the spacecraft needs 49,000 kilograms of antimatter and matter for annihilation, 98,000 kilograms total, including fuel. Producing 49,000 kilograms of antimatter is absurdly beyond current capability. Fermilab's antiproton production achieves about 10 nanograms per year. At this rate, producing 49,000 kilograms requires 5 times 10 to the 15th years, 350,000 times the universe's current age. CERN produces about 1 nanogram of antiprotons per year through particle collisions. The production efficiency is roughly 1 part in 100,000. For every 100,000 protons accelerated, 1 antiproton is captured and stored. Each 100,000 protons requires about 10 trillion electron volts of energy. Producing 1 kilogram of antiprotons requires roughly 10 to the 26th proton accelerations, consuming about 10 to the 21st joules, roughly equal to 200 times world annual energy consumption. And this produces only 1 kilogram of antimatter, enough to accelerate less than 2 kilograms to 0, 99c, including fuel. Photon rockets directly converting mass to photons expelled as exhaust represent the theoretical maximum efficiency. Such drives have exhaust velocity c and could achieve the velocities given by the relativistic rocket equation. But building a photon drive requires technology far beyond current capability. Possible mechanisms include matter-antimatter annihilation, producing gamma rays directed through magnetic nozzles, or black hole evaporation directing Hawking radiation. Both face enormous engineering challenges. Even if built, photon rockets are limited by the rocket equation. 90% of the spacecraft must be fuel to reach 0. 98c. Beamed propulsion offers a potential solution. Keep the power source stationary and beam energy to the spacecraft using lasers or particle beams. The spacecraft carries a light sail or particle collector, gaining momentum from incoming photons or particles without carrying fuel. This eliminates the rocket equation's exponential mass requirement. But beamed propulsion faces its own challenges. Enormous power requirements for the beaming station, beams spreading over interstellar distances requiring enormous mirrors or lenses, and the need for infrastructure at the destination to decelerate the spacecraft. The Breakthrough Starshot project, announced in 2016, proposes a laser-pushed light sail reaching 20% of light speed. The plan: launch gram-scale spacecraft with square-meter sails, illuminate them with ground-based lasers, totaling perhaps 100 gigawatts for several minutes, accelerating them to 60,000 kilometers per second. At this velocity, travel to Proxima Centauri takes about 20 years. But 20% of light speed is far from the 99.9% needed for relativistic travel. And even this modest goal requires technology decades away. Scaling to higher velocities requires proportionally more power and encounters diminishing returns as velocity approaches c. Deceleration adds another energy requirement equal to acceleration. A spacecraft accelerating to 0.99c and decelerating at the destination requires twice the energy accelerate once, decelerate once. If beamed propulsion isn't available at the destination, the spacecraft must carry deceleration fuel, doubling the mass ratio requirement. A round trip requires 4 acceleration, deceleration burns, and if fuel must be carried for all of them, mass ratios become absurd, exceeding 1,000 or 10,000, making the spacecraft essentially entirely fuel with minuscule payload fraction. The Fermi paradox asks, if intelligent life is common in the universe, where is everybody? One answer: interstellar travel is impossibly difficult due to the exponential energy requirements near light speed. Even civilizations, millions of years more advanced, might be unable to reach relativistic velocities economically. If the energy required to send one spacecraft to another star exceeds what entire civilizations can muster, the galaxy remains unexplored despite abundant life. The light speed barrier might be an insurmountable filter, explaining why we see no signs of galactic colonization despite billions of potentially habitable planets. Some argue that advanced civilizations might harness stellar energy-building Dyson spheres, capturing a star's entire output, providing sufficient energy for relativistic travel. The Sun's total power output is 3.8 times 10 to the 26th watts. Capturing this for 1 year gives 1.2 times 10 to the 34th joules, enough to accelerate 6.3 million tons to 0.999c. This seems substantial until considering the need for numerous spacecraft, infrastructure, deceleration fuel, and losses. Even Kardashev Type II civilizations, utilizing entire stars, might find relativistic interstellar travel economically prohibitive for colonization, limiting expansion to slow, multi-generational subluminal journeys. The energy requirements expose why faster-than-light travel is more than just a special relativity issue. It's an energy issue. Even if special relativity could somehow be circumvented through exotic physics like Alcubierre drives or wormholes, the energy requirements for creating and maintaining these structures dwarf the energy needed for conventional acceleration. The Alcubierre drive requires Jupiter mass energy. Wormholes require similar or larger amounts. These energy scales are so far beyond any conceivable technology that faster-than-light remains firmly in science fiction, separated from science by unbridgeable energy chasms. The fundamental limit built into space-time itself, the speed of light, is not arbitrary. It's a fundamental constant woven into space-time's structure, determining how cause and effect propagate through the universe. The value 299,792,458 meters per second depends on our choice of units, but the existence of a maximum speed is unit independent. In natural units where c equals 1, the physics becomes clearer. Space and time are measured in the same units, and the speed limit is simply the rate at which cause and effect propagate through space-time. This maximum rate exists because space-time has a metric and mathematical structure describing distances and intervals with specific mathematical properties that enforce a speed limit. The speed limit emerges from the structure of the Lorentz transformations and the requirement that physical laws be the same in all inertial frames. If we demand that Maxwell's equations hold in all inertial frames preserving electromagnetic phenomena, we must accept Lorentz transformations that mix space and time. These transformations have a fundamental velocity scale that leaves light speed invariant. No other transformation law consistent with relativity and causality exists. The speed limit is a logical necessity given that physical laws don't depend on uniform motion. The fine structure, constant approximately 1 divided by 137, connects light speed to fundamental electrical properties. This dimensionless constant equals E squared divided by 2 times epsilon 0 times h times c, where E is electron charge, epsilon 0 is electric permittivity of vacuum, h is Planck's constant, and c is light speed. The fine structure constant determines the strength of electromagnetic interactions. Its value affects atomic structure, chemical bonding, and electromagnetic phenomena. The fact that this dimensionless combination equals approximately 1 over 137 is a deep mystery. Why this particular value? Light speed relates to vacuum permittivity epsilon 0 and vacuum permeability μ0 through the equation C equals 1 divided by the square root of epsilon 0 times μ0. These constants describe how electric and magnetic fields propagate through empty space. Epsilon 0, approximately 8.85 times 10 to the minus 12th farads per meter, measures how much electric field exists for a given charge distribution. μ0, defined as exactly 4 pi times 10 to the minus 7th henries per meter before the 2019 SI redefinition, measures how much magnetic field exists for a given current. Together, they determine light speed. Why do epsilon 0 and μ0 have the values they do? This is equivalent to asking why light speed is 299,792,458 meters per second rather than some other value. The answer: in our system of units, the meter and second, these are the values that match physical reality. But in natural units where c equals 1, the question disappears. The real question becomes, why does spacetime have a Lorentzian structure rather than Galilean structure? Why is spacetime described by Minkowski geometry with its light cone structure rather than Euclidean geometry with absolute time? These questions probe the deepest levels of physical law. Causality fundamentally requires a maximum speed. If influences could propagate arbitrarily fast, effects would be simultaneous with causes regardless of distance. Every event would be in every other event's light cone. The distinction between past and future would collapse. The universe would be static, or rather, the concept of dynamics would be meaningless. A finite maximum signal velocity creates the light cone structure that defines causality. Causes precede effects. Effects are confined to future light cones, and space-like separated events cannot influence each other. The speed limit is the cornerstone of temporal ordering. Information cannot propagate faster than c. Because information is physical, it requires energy or matter to encode and transmit. Any physical system, obeying local physics, where interactions occur at specific locations in spacetime, automatically respects the light speed limit. Non-local theories where distant events instantaneously affect each other would violate causality, allowing signals to the past in some reference frames. The requirement that information propagation preserve causality in all reference frames forces information to travel at or below c. This applies to all information regardless of encoding: electromagnetic signals, massive particles, gravitational waves, or hypothetical new forces. The speed limit affects every physical interaction. Electromagnetic forces propagate at c through photon exchange. When an electron moves, changes in its electric field propagate outward at c. Distant charges don't respond instantaneously, but only after light travel time. Gravity propagates at c through graviton exchange or gravitational wave propagation. The 2017 observation of gravitational waves and gamma rays from a neutron star merger arriving within 1.7 seconds after traveling 130 million light-years constrained the difference between light speed and gravitational wave speed to less than 1 part in 10 to the 15th. Gravity propagates at c to extraordinary precision. The strong and weak nuclear forces also respect the light speed limit. Quarks interact through gluon exchange, and gluons propagate at c. The weak force operates through W and Z bosons, also propagating at c. No known force, fundamental or emergent, propagates faster than c. If any force violated the speed limit, it would enable faster than light signaling, creating causality paradoxes. The consistency of physics across all forces and interactions suggests the speed limit is a universal feature of physical law, not a property of specific forces, but a property of space-time itself. Quantum mechanics respects the light speed limit despite apparent non-locality from entanglement. The no-communication theorem proves that quantum correlations cannot transmit information faster than c, preserving causality. Quantum field theory, the merger of quantum mechanics and special relativity, enforces causality through the requirement that field operators at space-like separated points commute. This mathematical requirement ensures measurements at one location cannot affect measurements at space-like separated locations, preventing faster-than-light influences. The marriage of quantum mechanics and relativity is logically consistent, both theories respecting the light speed limit. The speed limit's universality suggests it's not a technological barrier, but a fundamental feature of reality. No matter how advanced technology becomes, nothing can exceed c without violating causality or requiring infinite energy. Science fiction often handwaves this through hyperspace, subspace, warp drives, or other mechanisms, implicitly assuming physics beyond Einstein's relativity. While general relativity allows exotic geometries like wormholes and Alcubierre drives that achieve effective superluminal motion, these require exotic matter violating energy conditions and probably cannot exist according to quantum field theory. The anthropic principle offers one perspective on why c has its particular value. If c were much larger, say, infinite in the Galilean limit causality would be problematic, possibly preventing complex structures like life from forming. If c were much smaller, say, 100 meters per second, relativistic effects would dominate at everyday velocities, potentially making chemistry and biology impossible as we know them. The observed value might be one of limited ranges, compatible with observers existing to measure it. This argument remains speculative, but highlights that fundamental constants aren't arbitrary. They're constrained by requirements for complex, stable structures. String theory and quantum gravity approaches suggest spacetime might be emergent, arising from more fundamental structures at the Planck scale. In some formulations, space and time are not fundamental, but emerge from quantum entanglement or other pre-geometric structures. The speed limit might emerge as a low-energy effective description of more fundamental physics, where spacetime itself doesn't exist. Understanding why c has its value might require understanding how spacetime emerges from quantum gravity, a problem that remains unsolved despite decades of theoretical work. The light speed barrier has profound implications for humanity's cosmic future. If we remain confined to subluminal travel, the observable universe 5 billion light-years radius becomes fundamentally inaccessible. Even traveling at 99.9% of light speed, reaching the edge takes billions of years of proper time, and cosmic expansion carries distant regions away faster than we approach. We might colonize the local group of galaxies over millions of years, but the broader universe remains forever beyond reach. Accelerating expansion driven by dark energy will eventually isolate the local group from all other galaxy groups, leaving our descendants in an island universe surrounded by unreachable cosmic shores. Yet the speed limit also provides stability and predictability. If faster-than-light travel were possible, causality violations might occur, creating logical paradoxes where effects precede causes. The universe might be inconsistent, with contradictory histories competing. The light speed barrier ensures the universe has a well-defined causal structure where past determines future through local interactions obeying differential equations. This structure enables complex, stable systems like stars, planets, and life to exist and evolve. The speed limit that prevents us from easily exploring the cosmos might be the same constraint that allows the cosmos to exist in a form capable of supporting us.